Is everything up and running? Looks okay. Okay, should all be fine. Okay. I'll check the chat. Okay, cool. So this is going to be a revision session for paper 2 tomorrow for the A level, particularly for Edexcel, but the topics are most the same, but this is for Edexcel. So this is, as I said, revision. So what I've done, and also I recommend two things. Firstly, I recommend, because paper 1 was heavily based from, where's my pen? From June 2022. There it is. June 22, paper 1. So I think you'll get good practice first of all. If you practice June 2022, paper 2. Okay. And obviously that's not saying if they kind of resemble paper 1 June 2022, they're going to do the same for paper 2. Not necessarily, but it'd be a good practice either way. And actually I've already done not a walkthrough, but I went over the paper on my YouTube as well. I'll link that in the description, but it's also my A-level playlist, past paper playlist. But we're going to go over some more questions anyway. Some of them are from June 2022. So that's the first one. The second one is I also recommend watching my other revision stream, where I looked at some other questions, which I still think would be good as well. As a revision resource. And again, I'll link that in the description as well. So what have I done for this one? Well, I've compiled some more questions. So the topics that normally come up that haven't yet really. And so I've got them from various past papers, and I thought we'd go over it. And so I guess the strategy, well, not strategy, but the idea for this is hopefully you would understand what's going on, but if you don't, when I go over it or attempt it, then you can kind of like look into a bit more, right? And hopefully and try and understand what I'm saying. So then you do understand it, right? And also all the questions like here, there are I told the paper where it came from. So if you do want to look at a question in more detail, I told you where you can find it. Okay, and also this is 116 marks worth, so it's slightly more than I hope the paper's worth, which is usually 100. But I think these are good questions to go over. Okay, I'm going to stop waffling now. So question 1, we are given a curve with a function y is f of x. We are given that the first derivative is 2x and half cos x. The curve has a stationary point which is alpha, and alpha is small. Then it says for pi, use a small angle approximation for cos x to estimate the value of alpha. And actually, I've quoted it from the formula book here, the small angle approximations. Okay, so essentially, well, this for cos theta is going to be this one, isn't it? 1 minus theta squared over 2. So really, we can substitute that in. So f dash of x is going to be, well, it's going to be approximate to, and that's going to be 2x at a half, and cos x would be 1 minus. Apologies. So then cos theta is going to be 1 minus x squared over 2. Cool. And it says it's a stationary point, So that's going to correspond to the first derivative equal to 0, right? So this is going to have to equal 0. Okay, now we can just tidy this up to say, well, 2x add a half minus, well, x squared over 2 over 2. That's going to be a quarter, right? Equals 0. Okay, cool. Now this is a quadratic. So you could put it into the quadratic solver. But first of all, I'm going to tidy this up a little bit, get rid of the fraction. So this is the same as saying minus x squared, add 8x, but divided by 4, plus 2 is equal to 0. And then you can put that into some sort of solver, right, in your calculator. Or if you're unsure about, I keep saying this, but if you're unsure about, losing marks, not showing you're working out fully, you could just write the quadratic formula down, which should be fairly quick. So that would mean the x solution would be minus 8 plus or minus the square root of minus 8 squared, no, 8 squared, isn't it? Although it doesn't matter, it's the same. Minus 4, minus 1 and 2 over 2 times minus 1. Okay. And then, obviously, once you write that down, you don't have to use a calculator and write down the formula. Then you can just secretly, if you will, pull it into the quad solver, the solving your polynomial solver in your calculator, which should be a lot quicker. So minus 1 for A, 8 for B, and 2 for C. And so you get 4 plus 3 root 2, or 4 minus 3 root 2. And so that's going to be in decimal form because it's set to 3 decimal places. So that's going to be 8.2426, blah blah blah, or minus 0. For God's sake. Or minus 0.2426. For God's sake. And those are so minus 0.2426, and those are two solutions, thereabouts. Okay, but which one are we going to set? Because it's only one value. We can only have one solution. And it's going to come around the fact that the solution alpha must be small, which means it needs to be about 0 or close to 0. Well, it's going to be this one, isn't it? So I'm going to say alpha is small. So alpha must be minus 0.24, and then it'd be 3, right? 3 decimal places. Cool. Okay, and then we are told this point P lies on C. Find the equation of the tangent to the curve at P, give me the answer in this particular form here. Okay, so this is differentiation, because it's about tangent. But how would we work out a tangent? Well, you're going to want dy dx, right? And then substitute the point in. But we already know the derivative is given here, so we actually don't need to do that. So then we recall that f dash of x is 2x plus a half cos x. Okay, and then we need to substitute this point in to get a gradient. So well, it's going to be x is 0, isn't it? So then f dash of 0 is going to be 2 of 0 add a half cos of 0, which I think should be a half, but I'll double check that. Yes, a half. So that's our gradient. So therefore, our gradient's a half. So y equals mx plus c so that's the general equation of a line, and that becomes y is a half x at c. Okay, but how are we going to find C? Well, we are given a point that lies on the line, right? The tangent. Again, it's P03. So and then I'm going to say sub 03 into the line. So therefore we have 3 is going to be half of 0 at C. Well, then that just means C is 3, right? And there we are. We got the equation of the line of y is a half x add 3. Cool. Okay, question 2 now. We are given a sequence of numbers defined by this sort of recurrence relation. So we plug the previous term in here, and then we get the next one, and then it repeats like that. Okay, so we're given some information that it's periodic with order 3 and the first term. We need to show this. So with this sort of question in general, again, the best thing to do if it's an unknown sequence like this, just try the first few values in, plug the first few values in and see what we get. So we know that A1 is 2. But that's our starting one. So then what about the next term, A2? So then that's going to be K lots of A1. I'm not going to substitute in directly just yet. I'm just going to say it's A1. Then that's going to be K lots of, well, A1 is 2, add 2, over 2. So that's going to be 4K over 2, which is going to be 2K. Cool. Okay, then that's A2. What about A3? Well, A3 is going to be then K lots of A2, which is going to be 2K add 2 over A2, which is 2K. And then that's going to be, if we expand this out, well, we can factor a 2 out. So that's going to be 2K lots of K and 1 over 2K. And then the 2K's cancel. Great. And that'd be left with K plus 1. Okay, then what about the next one? Because it's not, so the next term would be K lots of K plus 1 plus 2 over K plus 1. And again, let's expand, let's simplify first. So it's going to be K lots of K plus 1 plus 2, which would be plus 3 over K plus 1. We can perhaps expand it maybe to K squared add 3K over K plus 1. Cool. Okay, so those are those first few terms. Okay, then what about this? So it says the sequence is periodic with order 3. What that means is think about periodic. So think about how a sine curve if it has a period of 2 pi. That means it repeats itself every 2 pi. So it goes back to its starting point, if you will, at 2 pi when it repeats the shape again. Okay. It wouldn't be pi by the way because it's still going down. That's not the same shape because obviously it's going up here between 0 and pi, but then it's going down. When it repeats its shape, is at 2 pi and then it goes again. Okay, so the period is 2 pi. In the same sense, if it's periodic, the sequence repeats and it goes back to the same term. Okay, and then it repeats from there. So, but then how many times is that? Well, that's the order. So it says order 3. So, for example, if we have an order 3 means it has 3 different terms before then it repeats back. So, for example, 7, 5, 1, and then it goes back to 7. No, sorry. Yes, that's a period of order 3 because there's 3 numbers, 3 terms before it goes back to 7. So what that means in this case, well, if it's period order 3, then A1, A2, A3, A4. Well, the first 3 terms are going to be different, and then it goes back to A1. So that means A4 has to be equal to A1. And so that's what we can deduce. But we know an expression for A4, don't we now? We worked it out by substituting the first 3 terms in. So then that's going to say, well, K squared at 3K over K plus 1 is going to equal A1, which was given to be 2. Okay, now we need to get some sort of quadratic. So we can firstly just cross multiply, get rid of the k plus 1 denominator. So then k squared at 3k is going to be 2 lots of k at 1, which will be 2k at 2. Then I can move it to then say k squared at 3k minus 2k would be k. Minus 2 equals 0. That is the quadratic. Lovely. There we are. See, so the strategy of that sort of thing, it looks a bit weird at first. Like, how am I going to get this random quadratic for k? But then just play around with it. Just get the first few terms and then see what you can do with it. Okay, that's the general advice for unknown sequences like that. Okay. Okay, part B then says, so I'm going to do part B here. Why can k not be 1? So if I was to solve this then, we could actually factorize it because 2, obviously it's either 2 or 1. But if we times by, then we could take positive 2 and minus 1. It factorizes to k minus 1, k plus 2, right? Therefore, you'd say k equals 1 or k equals minus 2. But we cannot take k is 1 as a solution. Why is that? Well, it's not explicitly clear because it is a solution, right, to the quadratic. Um, so I guess Len, if you're unsure about if a solution is correct, or say for example, and we'll go over another case like this later. But say for example we square something, that introduces an extra solution that might be wrong. What you can do then is you check the solution to the original part. So let's try substituting k back into the original sequence. So then an plus 1 is going to be, well, k is going to be 1, so it's just going to be an plus 2 over an. Okay, then let's see what happens. So a1 is 2, that's given. So then a2 is going to be 2 add 2, which should be 4 over 2, which should be 2. Okay. Well, then it's just going to keep repeating, isn't it? A3 then is 2, A4 is 2. So we get 2, 2, 2, 2 is the sequence. Okay, but but that cannot really be what we want because because like I said, it needs to be 3 different terms, right? For have it to be periodic with order 3. Like we said, we need 3 different terms before we go back to where we started from. But here it's just always 2. And this is where it gets a bit technical, but this still has a period of order 3, technically, because it goes back to 2 after 3 times. But it also has an order period of 2, because then it goes back after 2 times. It also has a period of order 1, because obviously it goes back after just 1 term. It has multiple orders, that's the thing. So technically, this sequence is periodic with order 3, but what we actually do mean by it is it has to be different numbers, and we want the minimum order. Okay, so when we say order 3 for the sequence, we want the minimum order to be 3. Okay, so we want exactly the first 3 numbers have to be different, and then we repeat back after the fourth term, right? So I'm going to say this is not. So I'm going to say the sequence does not have, and you could say minimum, but I'm just going to say a minimum periodic order of 3. So k cannot be 1. Okay, hopefully you can recognize that it does actually satisfy it, right? It does have a period of 3, but also have periods of 2 and 1, and actually 4, 5, 6, 7, 8. But we want the minimum one, right? But the minimum is just going to be 1 for the order here. That's not really what we want. We want an order of 3 at the minimum. So that doesn't satisfy it. Okay, cool. So that's our sort of reasoning, right? So that's the sort of strategy. If you're unsure about stuff like that, try and substitute it in, see what happens. Okay, part C then, again, pretty classic. Then we want to find this summation here of 80 and R equals 1 of AR, I think. Yes, okay, so this is saying, so this is going to be sigma notation, which says we want to sum between R is 1 and 80. So plug R is 1 and R is 2 and R is 3 and what so on. So we're going to have A1, then we're going to add A2, then we're going to add A3, then A4, and then so on to the last term of A80. Okay, that's what that's saying. Okay, but so we kind of need to work out what all these are, right? A1, A2, A3, A4, in order to add them. But it's all in terms of K, like we did in part A. So I'm gonna say A1 is 2. A2 was 2K for pi. And I think A3 was K plus 1, was it? I can't remember. K plus 1, yes. And then A4, as we discussed, was back to 2 because it has a period of 2, of 3, sorry. And then therefore A5 will be A2, A6 will be A3, and so on. But this is in terms of K, but not a number. But we already know what K is already now. We worked that, discussed it. It's up here. So I'm going to go back to saying from part B, K is 1 or K was minus 2, but K cannot be 1. So can only be minus 2. Okay. From solving the quadratic. Well, then therefore A2 then is going to be minus 4, 2 times minus 2, and A3 is going to be minus 2 add 1, that'd be minus 1. Okay, so then therefore the sum then, so well this sum here 80, R is 1, AR, that's then going to be A1, which that's going to be 2, and then we're going to add and then A2 was minus, but we're going to add minus 4. Okay. I'm going to write it like this. Then we're going to add minus 1, and then we go back to 2, and then we add minus 4 again, then we add minus 1, and so on to the last term, A80. I'm not entirely sure what A80 is going to be yet, but that's fine. Okay, and the strategy with this sort of question is you need to spot the pattern, be able to split the sum up. Now, we can't just, because there's 3 terms, it's really only repeated between 3 different terms, right? You can't really split 80, because it's going to be 80 sums, right? 80 terms to add up over 3, because that's a decimal. Okay, so that's going to be really awkward to work with, because you can't have a decimal of a term. So the strategy we can do instead is say, let's go back from 80. Let's go back to the 79th term. Is that divisible by 3? No, 79 divided by 3 is still a decimal. Okay, then let's try 78. And 78 should be, I think. 78 divided by 3 is 26. Yes, now we've got a whole number, which means we can exactly split this term, the 78 terms between 3. Exactly. What we can then say, well, we can split this up then. So that's going to be between 78 and R is 1 of AR. And then what we could do then is just add the last 2 terms, A79 and A80. And then we can work these out individually. Okay, so then 78. So we're going to divide. So we notice there's going to be equal amounts of 2 minus 4 minus 1 in the sum. So we can split them up. 78 divided by 3, which is 26. So going to be 26 lots of 2. And then there's going to be 26 lots of minus 4. And then there's also going to be 26 lots of minus 1. Okay, so that's this bit dealt with. Now we need to deal with these 2 terms at the end. Okay, so 78. So A78 is going to be A3, isn't it? Okay, because that's going to be the end of the this summation here. Hopefully you can see that because it's going 2 minus 4 minus 1. And then if we're going to split it into 3 times, the end one is going to be minus 1 as well. Okay, to ensure we can group them into 3. Hopefully you can kind of see that though. But yeah, so once we realise that, well, A78 is going to be A3. That means A79, again, it's going to go back to A1 after A3. So that's going to be A1, and A80 is going to be A2 after. But we know what A1 is. A1 is going to be 2. So A79 is also 2. And A80, A2, but A2 is minus 4. So then that's going to be minus 4. And now, this is just a summation, right? We can just put this into a calculator. So that's going to be 26 lots of 2. Well, you can actually just combine it together. Say 26 lots of 2 minus 4 minus 1, and then add 2 minus 4 at the end. And that gets minus 80. Okay. And that should be our sum. Cool. So that's really a good strategy, right? With these sort of summation questions like that. To split it up. So go down a few terms. If it won't be nicely divisible by like 3. The top number, the 80 terms you add in. So knock off a few terms, and then you can split it by 3 is equally, and then you can do it like this, okay? And then just add the last few terms at the end. Cool. Question 3 then. Given this logarithm here, show this quadratic. Again, it's pretty similar, I guess, in the idea of the last question with the case. So we're given some sort of thing and we need to show this quadratic. Let's just work with the thing, right? Let's work with this top bit here. And then we get to something in the end. Okay, pi I'm going to do here. So let's write this then. Log 2 of x plus 3, log 2 of x plus 10 is going to be 2 add 2 log 2 of x. Okay, so this is also going to involve log laws. So I think the first thing is because I have no powers in the bracket, so the only thing I really can use is log AB is going to be log A add log B. Okay, or subtract to divide. That's the main one, right? So I'm going to need to add the logs together. I'm going to have to bring all the logs together, right? So then I'm going to say log 2 of x plus 3, add log 2 of x plus 10, and then I'm going to bring this log to the left to get all the logs on one side, and that's going to equal 2. Okay, now I can use this log law, and also the other one of a divided by b is log a minus log b, to bring this together. So firstly, at log 2, bring them all in the same log. Well, if we add in these two, we're going to times what's inside together. So then that's going to be x plus 3, x plus 10. And then we're subtracting by 2 log 2x. However, we have a 2 here. So this is not exactly the right log law because they have to have the same coefficient outside the logs. Here the coefficient's 1, but here it's 2. Okay. But we know how to bring a number in front into the log, don't we? That's actually the power law. So log of a to the n is n log a. So we can bring the power in to the front into the log, right? What's in front into the log. But then therefore that's going to be log of x squared, isn't it? Because the 2 will go as the exponent. Okay, then we're subtracting, so it's going to be divided by x squared, isn't it? And that's going to equal 2. Okay, now, because we've got a single log like this, we can then raise it to the power of 2 log 2 of x plus 3, x plus 10 over x squared. And that's going to equal 2 to the 2, right? Because we're raising 2 to the power of each side. I can do that. I'm allowed to do that. Okay. Well, actually, 2 to the log 2, they cancel because they're kind of inverse of each other. Alternatively, recognize that e to the log, well, in general, a to the log x is just going to be exactly x. So inside what's the log, log a to the x as well. I think that's in the formula, but you do just need to remember that. It makes your life a lot easier. We by recognizing you cancel out like this. Okay, well then let me just left with, like we said, what's in the log. So it's going to be x plus 3, x plus 10 over x squared equals, well, 2 squared is 4. Okay, now this is quite nice, isn't it? This is a lot more simpler. So then that's going to be x, then I got times across by x squared, and that's going to equal 4x squared. Okay, and now we need a quadratic, so we have to expand this out. So that's going to be x squared, 10x and 3, that's going to be 13x, add 30 equals 4x squared. Therefore, then we can move it on 3x squared by moving f from the left to the right. And then minus 13x minus 30 equals 0. Is that what we got? 3x squared minus 13x minus, yes, great, cool. Okay, then part B says, let's do it here now. Write down the roots of the quadratic. Because it says write down, you don't need to show any method for it. They expect you to put it into the calculator, right, and write down the answer. So that's going to be 3 minus 13 minus 30 for the coefficients. We are going to get x is 6 and x is minus 5 over 3. Cool. Okay. Okay, that's for 1 mark, probably. Probably the easiest mark on an A-level paper. Then it says, which of these roots is not a solution to the equation? And the equation is identical, okay, if you compare to what we worked with. So, which of these solutions would not work, essentially? And then it goes all the way back to what I said before, earlier, about trying, if you're given something like this and you need to reject something like a solution, just plug them all in and see what happens and what happens. Okay, well, x is 6. So if we plug x is 6 into the equation here, well, that's going to be 6 of 3, which is 9. That's fine. 6 of 10 is 16. Then we get 6 in here. That's all fine, and that should work. Then what about minus 5 over 3? Well, that's going to be about minus 1.6. So minus 1.6, that's going to be like plus 0 point something. That should be okay. X plus 10, that's going to be minus 1.6 and 10. That's going to be 8.4 something, I think. That's okay. Okay, then log x, well, log x is minus 5 over 3. We cannot have a negative in the log. So I'm going to say log 2 of minus 5 over 3 is undefined. And you could try that in the calculator. Because obviously this sort of log graph, right? This is sort of the log graph at 1. It goes negative, but you can never have the x input be 0 or anything less than. So logs are never defined for 0 or for a negative value. So it's undefined. But then therefore we can't have it. So it's undefined. So x simply cannot be minus 5 over 3. And that's really it. There we are. That's really all we need to say. Cool. And that's a very common thing as well. They ask you to, you're going to need to probably reject the solution to like a logarithmic equation. Just check all the inputs of all the logs, and you're probably one of them probably be undefined, and therefore you're going to have to reject it. Okay. But yeah, cool. Question 4. Okay. Okay, so we're given a sketch of this curve here. Okay, the point P is a local maximum. You can see that here, it's a turning point. And then we need to find the x coordinates. So if it's a turning point, let's go back to question 1. We're going to need to find the solution to f dash of x is 0. Well, first of all, f dash of x then, of f of x, well, 8 sine of a half x. Well, sine will go to cos, and then a half x, we're going to times by the differential inside, which should be half. So 8 times a half is 4, so it could be 4 cos of a half x, okay? And then minus 3x will just go to minus 3, and then 9 will go away because it's a constant. And that's a derivative. So therefore we need to set that to 0 to solve it. So then 4 cos of a half x is going to be 3. So then in cos of a half x is going to be 3 over 4. And now we need to solve it. And obviously people might have the different methods, but I think just looking at the cos graph is the best way. So let's have a look. So a general cos graph is going to look like this. Okay, we need to see where 3 over 4 is. So it's going to be about here, isn't it? And that's going to be one solution. And then the other solution is going to be here. And I notice it's going to be the distance between 0 and this solution here is going to be the same distance when it repeats again, 2 pi, and this distance here. So it's going to be 2 pi minus the first solution, right? If this is the first solution. Okay. Anyway, we'll get to that in a minute. So to find the first solution, you're just gonna the angles are half x. So we're gonna arc cos it. We're gonna inverse cos 3 over 4. Make sure it's in radians. And that's going to give me this number here, 0.722734, blah blah blah. Okay, and then the next solution, like I discussed. Well, the distance between 0 and the first solution is that. Well, the distance is going to be this, isn't it? Because this minus 0 is still that. Okay, then therefore the next solution is going to be 2 pi take away this. Okay, so then that's going to be 2 pi take away that 0.72, and that's going to give me 5.560451.059. Okay, do we need any more? Let's have a look. Then the next solution would be adding 2 pi to all of them, okay? Because obviously it repeats every 2 pi. Let's have a look. Okay, let's have a look at our graph. Well, P is the turning point, cool. Let's have a look. But actually, there's a turning point here, and there's another turning point here. Remember when it whenever a tangent is obviously going to be 0, so it's going to be flat like this. That's a turning point. Hopefully you'll be able to spot them. So actually P is actually the third turning point. So actually we need the third positive solution, right? So we need the third solution to this. So then we're going to need to add 2 pi to this initial solution here. So the next solution is going to be oh, then we're going to add 2 pi to the first bit, so that's going to give me 7.00591955. Okay, then I'm going to say, well, P is the third turning point, isn't it? As we just saw, TP for turning point. Therefore, half x is going to be 7.00591955. Okay, well then that's a half x. Then to solve for x, we just times by 2. So that's going to be 2 lots of that. And that's going to give me 14.01183911, blah, blah, blah. To three significant figures, it's going to be 14 point... this is an awkward one, okay. I think it would be 0 to 3 sig figs. Okay. I don't know why. Of course, I'm stuck on the rounding bit. But normally 0 would be an insignificant one. But uh, but I think it's it's in between. It's already in between significant digits, so it by itself becomes significant. I don't know, but that is the answer. But I guess I was right there, but it was a little bit of a guess. I cannot believe I did all of that right, and then I got stuck on the significant figure. Makes you see, even the basics you need to know. You know. Anyway, of course, that's right. The main bit here is to recognise it's actually the third solution because it's the third turning point away from 0. Okay, and these are turning points. Okay, when the graph dips like this, um, when it goes from increasing to decreasing or decreasing to increase, they're all turning points. Hopefully, you should be able to spot them though. Okay, cool. Then it says the curve crosses the x-axis at x is alpha, which is actually also shown on the graph here. Okay. Given that 3 decimal places, f of 4 is 4.2 something, and f of 5 is minus 1.2. Explain what must lie in this interval 4 to 5. Well, it's just sign change, isn't it, really? So there is a sign change for just one mark as well between f of 4 and f of 5. And we are missing something else, aren't we? And this is the key bit you need to remember. The function is continuous. That is another key assumption there between locating a root like this. Because if it's continuous, you never take your pen off the page, essentially. So if we have 4 and 5 here, where it goes from positive to a negative, the only way we can start here and end up here without putting a pen off the page is to cross the axis, right? There's no other way. You can try to do jiggy bits, but at the end of the day, you're going to have to cross it to get to 5. So you have to have a root in between. If it's discontinuous, then we can write it off the page informally. But that essentially means there's like discontinuities, like the graph jumps. For example, of a cyclical graph, it's discontinuous at 0. So, for example, say if we went that way, oh, no, say like this way, and then halfway through, there's some sort of asymptotal in discontinuity, and then the graph jumps down here. Well, actually, there would be a sign change. We just calculate f of 4 and f of 5. However, because there's a discontinuity, it's jumped on the graph. It doesn't actually pass through the axis, so there wouldn't be a root despite a sign change. That is why you have to include it's continuous. To also conclude there is a root. So I'm going to say that therefore there is a root in 4, 5. Okay, in the interval 4, 5. More specifically, it doesn't have to be continuous, the whole time. It just has to be continuous in the interval. So, say for example, again, there might. I'm only saying this for the extreme cases, in case they might catch you out. Um, Say for example, it's between 4 and 5 again. It is continuous, as we discussed. Cool, like this. But then it could be discontinuous outside the interval. And we know there's a root in the interval, as we discussed. But say there's, again, a discontinuity between here, right? But that wouldn't affect the fact there's still a root in the interval, despite discontinuity outside the interval. So, as long as it continues specifically in the interval, um, then it's continuous, and therefore there is a root. Okay, that's more specific. But if it's continuous, then it's going to be continuous everywhere. as you can see here, so it still be continuous. But I'm just saying that's an extreme case because they might give you discontinuity, but then actually, as long as it's still continuous in an interval, you'll still be grand. Okay. That's just really not specific detail there, in case to catch you out, but it should be okay. And yeah, is there anything else I want to say about that? I feel like there was, but I can't remember. Uh, don't know how it'll come to me. But anyway, we've got this part B, part C, sorry. Then we have x0 is 5. We need to apply Newton-Raphson to solve to find alpha. Okay, well, the Newton-Raphson is given in the formula book, and it's stated like this. I copied it from the formula book. So we need to solve f of x is 0. Well, f of x is this bit here. Again, is 8 sine of half x minus 3x. 39, 3x over 9, wasn't it? Equals... Yes, and if it's a root, then also it's going to equal 0. Okay, cool. So that's f of x. Then we're going to need, let's go back to a formula. To basically substitute it in, we're going to need f dash. But we know what f dash is. We already computed the derivative in part A. That will go to 4 cos x minus 3. Right? Again, look at part A that we did here. But yeah. So now we've got all the ingredients, right, to use Newton-Raphson. We can substitute it in. Therefore, Newton-Raphson, xn plus 1, copying it in. It's going to be xn over f of xn over f dash of xn. So then that's going to be xn plus 1 equals xn minus, and then I'm going to replace the function in. So it's going to be 8 sine of a half x minus 3x add 9. All over 4 cos x minus 3. So then I put the derivative on the bottom. Okay, cool. Well, then it's like a iteration, right? So I'm given the first point. I then need to apply it once, okay, to find the next approximation. So if x0 is 5, was it? Yes. But then therefore, x1 is going to be x0, which is going to be 5. Minus 8 sine. Oh, that should be xn as well. xn. Okay, cool. Because you're replacing obviously the previous x to get the next. Anyway, so then that's going to be 8 sine over half of xn. That's going to be half of 5. So that's going to be 5 over 2. Okay. Minus 3 times 5. I'll just leave it as 3 lots of 5 and 9. Okay. And then that's going to be 4 cos of x. That's going to be half x, isn't it? No. So that's going to be half x for cos, not x. There we go. So that's going to be cos of a half x and minus 3. Okay, cool. Did I compute? I should have, because we did check the answer. Yeah, half. I don't know. I just forgot the half. So then that's going to be 4 cos. Again, that's going to be 5 over 2. If you substitute half times 5, and then that's going to be minus 3. And now these are all numbers. We should put it into the calculator. So that's then going to be 5 minus 8 sine of 5 over 2 in radians still. Minus 3 times 5, add 9. About 4 cos 5 over 2 minus 3. That would get me this number here, 4.8046. 24337, so on. What's it rounded to? Does it say? Give it to 3 significant figures. So therefore, x1 is equal to this 3 significant figure business again. It's going to be 4.80 to 3 sig figs. Okay. Again, I assume because the 0 is in between, well, it's after significant figures, so we do have to include it after. Anyway, so that's 3 sig figs, blue rounding. But yeah, that's the method. Fairly straightforward. The key thing with this, again, I'm going to reiterate once more. we have three turning points here, and then here, so the third solution. And you need to remember it's continuous as well as a sign change in part B to conclude as a solution in the interval. Okay, question 5. I've done this question loads of times now, but A, I think it really is a good question. And B, I think it will come up a question like this in the paper. So I thought, you know what, might as well. Most of the Trapezium rule questions are kind of the same anyway. But anyway, and also I did do it wrong actually last time. I did it right, but I had to. I took one of the y values the wrong as wrong. So actually, last time I did do it, I did it a little bit wrong. Didn't get the right answer because I just copied it right. There was error carried forward, so I would have lost on a mark. But you know, this time I'm going to redeem myself. Anyway, now we're given a table, and then quite usual, we're given data for various x and y values. We need a trapezium rule to estimate this. Okay, so let's just rewrite this as not rewrite, copy it as log 3 of 2x. Okay, cool. So the trapezium, again, I copied it here. It'll be like this in the formula book. We need this h bit first before we substitute it in. So h is going to be b minus a. That's going to correspond to the upper and the lower limits. It's going to be 9 minus 3 over n. Okay. So that's going to be 6 over n. But what is n then? So n, again, it's going to be about, the way this works is splitting this into trapeziums. So we have this sort of curve here. Say if f of x looks like this. Essentially, we're going to say we sample it between like 3 here and then 4.5 and then 6, and they have all equal width, although they look a bit off. 6 and then 7.5 and then 9 at the end here. Essentially, they're all trapeziums, right? Oh, okay. And that's what we're doing, just constructing, well, I'm doing it really badly, but trapeziums, and the n is corresponding to how many strips or trapeziums we have. So here's going to be 4. So then you could say well, n is 4, because we construct 4 trapeziums with these sort of points we have. And there will always be one less than the points we have. So we have 5 points in total. 1, 2, 3, 4, 5. So it's going to be one less. So it's going to be 4. However, I think a lot of people might struggle with that, or might not have time to realise in an exam. Well, the other way really is to use a formula to guide you, essentially, because look at what the formula's saying here. We are summing with the y values, which are here. We start at y0, so obviously the first one's going to be y0. Then it goes up to yn, and that's the last value of y. That yn is going to correspond to the final y value. So if we start from y0, then y1 is going to be this, y2 is going to be this, and y3 is going to be this. Well, y4 is the last one. Well, but you said yn's the last one, so therefore n has to be 4, which is what we got here. So that's a nice way of looking at it if you really are struggling. To just count how many values you have. But yeah, okay, cool. So we found h, and we know our y values here. Now we can just substitute it in. So therefore, the integral, I'm just going to be lazy here. That's going to be approximate to a half of h, which is going to be 6 over 4. That's just simplifies to 3 over 2. So I'll just write that there. And then we are times, and then first of all we have to add y0 and yn, so that's the n values, so that's y0 and that's yn, so that's going to be 1.63 to 2.63, and then we're going to add 2 lots of everything else. Okay, so y1 to yn minus 1, which is y3, so then that's going to be 2 lots of 2.26. Last time I misread, that's 2.6. I don't know why. And 2.46. Then we put that one into the calculator to get this fraction here, 531 over 40, and that's your approximation, your estimate. Cool. So that's just using using the trapezium rule. Okay, mostly it's sort of the same sort of thing. But yeah, hopefully that you should be aware now. Again, the hardest thing probably for most people is spotting what value of n you need to pick. But like I said, use the formula to guide you. Count how many y values you have. The n one has and start from 0. Then n is the last one. Anyway, so that's part A. Then part B, and this is why I like this question, although probably it's why most people don't like it. Part B, then is you're going to use some log rules to kind of transform or manipulate the original integral. So, and again, I think they're going to do that in the next paper. It's good to kind of learn. So first of all, 9/3 of log 3 of 2x dx. Well, we have 10 dx, don't we? Well, this screams the power rule, doesn't it? Where you can bring the power inside the log to the front. So then that's going to say between 9 and 3 of 10 log 3 to the 2x, right? Well, then I can bring, because 10's a multiple, I can just bring it outside the integral. Isn't that then identical to log 3 2x that we worked out in part A? So then that's going to be 10 lots of 531 over 40, which should be 531 over 4, right? And there we are. Cool. Okay, then part 2, the second one. Then we're going to need to estimate this. So log 3 of 18x dx. Okay, well, there's no power law here, so the only way is to kind of split them up. So we're going to need, we have a product here. We're going to need to split up the log like this into two different logs. How are we going to do that though? Well, and bear in mind, we need 18x. If we compare, right, if we then compare with the original, we have a 2x here. This is 18x. So we kind of need to, we have a product and we need it in 2x. Well, I think therefore I can split 18x into 9 lots of 2x, can't I? Because then it's, we have the 2x that we want and we made a product of 9. So then that's going to be log integral, sorry, of 9 and 3 of log 3 of 9 times 2x dx. And then we can use this log rule. Because we have a product in the log, we can split it into two different logs. So then that's going to be between 9 and 3 of log 3 of 9 add dx dx. The integral of 9 of 3 of log 3 to the 2x dx. And now this is the identical integral part A. So firstly we can say that's 541 over 40, I think, wasn't it? In part A. 531 over 40, not 41. Okay, cool. But then what about this integral? Well, actually, you could. Well, you can't put the whole integral in the calculator. You do need to show it, but you can because this is an actual number, log 3 of 9. You could put that log 3 of 9 into a calculator, and it would simplify it. You would then get 2. So this is then plus the integral of 9 3 of 2 dx. However, you can see this because log 3 of 9. Well, that's simply log 3 of 3 squared, isn't it? But then the 2 goes in front. So then you're left with 2 log 3 of 3. That will cancel just 1. So 2 times 1 is 2. Anyway, there we are. But we know how to integrate 2D. We know how to integrate a constant like this. That's just going to be 2x, isn't it? Between 9 and 3. Therefore, that's 531 over 40. Add 2 lots of 9 minus 2 lots of 3. So you substitute the upper limit and subtract by the lower. Then you put that into a calculator. Well, that's going to be this fraction here. And there we are. Okay, I am going to double check it this time, but I think I should be okay now. So hopefully I got that right. Uh, du- 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 du. Uh, du- 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 du. Yes, I should be fine now. There we go, get in. Got it in the, yes, got it right now. Put the right numbers in. Okay, cool. So make sure you are comfortable with question. This came from 2022 paper 2. And bear in mind what's at the start that might resemble some of that paper. So it's good you know how to do that sort of question. Okay, cool. Question 6 then. Uh, have a read. This is a vectors question. So obviously a vectors question already came up in paper 1. It wasn't the biggest vector question though. And again, in paper June 2022, there were 2 vectors, one in each paper. So there might be another one now. Uh, I, I can't predict what sort of question. It won't be like a shape one because it already came up. Like you have to prove what was it? A certain triangle was right angle, something like that using vectors. So there might be no one be anything like that, but it might be some other stuff. This could potentially. Well, it might not be this one, but it's still good to practice vectors. That's why I threw this question in. It's a nice little vectors question to practice. So let's have a look. So we are given 3 points on the line. They all have these position vectors. And then Q lies 1/3 of the way from P to R. So with all these sort of vectors question, you should sketch what's going on. So we have this line PQR. Well, Q is going to be in the middle, right? Not in the middle, but somewhere on the line. But we're also told that Q lies 1/3 between, so it's going to be about here, isn't it? So that's going to be like one part, and then this is going to be 2 parts, isn't it? What we can say from that is P to Q. That's going to be 2 lots of Q to R, but then the total is PR, isn't it? So then that's going to be, oh no, a half, sorry, of Q to R. But that's also going to be a third of the whole P to R, because it's a third, right? P to Q is 1/3. Okay, what can we do now? Well, I think the best, we could use either equation, right? This is the only thing we can really use. I think it's best to say PQ is a third PR, right? For 2 reasons. Because firstly, there's already a third in the answer. But also, we only have one Q, so it should make our life easier to get this Q at the end here. Okay, well, this is where then the position vectors are going to come into play. Because it looks nasty at the moment, but we simply, for any vector AB, that's just B minus A, isn't it? So with that in mind, uh, PQ is simply going to be Q minus P. It's going to be a third of R minus P, isn't it? Then therefore to rearrange Q is then going to be P, and then we're going to, oh, that's a 3, don't know what that is. P, and then we're going to add a third, we can expand it, so a third lots of R minus a third P. Um, and then we can simplify the P bit, so Q is going to be, well, P minus third P is 2/3 P. Add a third R, and then we can factorize. So take a third out, and that's going to be 2P add R. And that's what we got. We got R plus 2P or 2P plus R. There we go. Nice little free marker that is. But hopefully that is sort of the method, right, to sketch it. And also, if you're given stuff on the straight line, I did this for GCSE as well. The people just did GCSE when the vector questions. Make you can conclude that you can make vectors out of them and that they're parallel. But here, that's all we needed to do. Okay, cool. Nice little vectors question. Again, don't neglect that. They might come up again. Question 7 now. There's some binomial expansion question. Then it says find the first 3 terms of the expansion of this. And what I did was copy. the binomial series formula. So which one are we going to use? Well, the first one is the AS one, but notice this here, the n. That actually means it's a positive integer, so it's 1, 2, 3. When the exponent outside the bracket is a positive integer, right? But we can't use that because we have a third. A third is going to translate to something of a half, isn't it? Well, a half is a fraction, not an integer, so that's out the window. So then we're going to have to use this. Okay. So we're going to use this, but we're going to need to make our bracket look like this: 1 plus x to the n. But here we have this weird third, so we're going to have to use some sort of index laws to simplify this. So let's say root 1 over root 4 minus x. Wow, that's firstly going to be 1 over 4 minus x to the half. But then that's a reciprocal, isn't it? So it's going to be 4 minus x to the minus the half. Now we're getting warmer. So let's compare. So we have 4 minus x to minus a half, but we need 1 here. It has to be exactly 1 that we're adding. So what we need to do then to make this 4 here go to a 1, we're going to need to factorize a 4 out. Okay, but let's do step by step. Let's not jump the gun if we're a bit stuck. We're not stuck, but a bit not as confident, right? Let's firstly, let's still keep it minus a half, but then let's factorize in the bracket itself. So 4, we can bring a 4 out, and then that'd be 1 minus a fourth x, right? A quarter x. That's before we dealt with this power outside. Okay, now it looks like it. 1 minus some lots of x. Great. Now I'm going to bring this power to these bits here. And I'm going to factor the 4 out entirely. Well, how am I going to do that? Well, you should recognize a to the mn. We can times the powers together. So it's like our GCSE, for example, if we had like 25 p to the 4 of a half, you would do it individually, wouldn't you? So 25 to a half, p to the 4 of a half. So then that's going to be p to the 2, and then 25 to a half is going to be 5, because it's root. It's kind of like what we're going to do here. So then I'm going to say that it's 4 to the minus a half, and then 1 minus 1 over 4x to the minus a half, bringing the power to both bits. Okay, cool. But I can evaluate this. 4 to the minus a half is, you can put that into a calculator, it's going to be a half of 1 minus a quarter x to the minus a half. Loads of halves. Okay, now, yes, we have a half in the front, but the actual bracket is resembling this, isn't it? 1 plus x to the n. And I need to charge this, hang on. Okay. Uh, okay, cool. So now I can do the expansion on this bracket part here. Well, to do that, I'm just going to use the formula, really. So that's going to be half. And then I'm going to do the expansion of this. Well, what is expansion going to be? So I'm going to need to essentially match what's going on to here. This bracket here, 1 plus x to the n. So here, well, I'm going to call this big X because there's already an X here. But big X here, what I'm going to substitute for X is going to be actually minus a quarter X. Okay, hopefully you notice that. If you compare 1 plus X in that is now 1 minus a quarter X. So hopefully you know why I have to take minus a quarter X. And n, the power outside is minus a half. So n is minus a half. Well, therefore the expansion then, we're just going to copy here, aren't we? So it's going to be 1 add nx, so n is minus a half. And remember, x now is minus a quarter x. Then we're going to have n of n minus 1, so that's going to be minus a half. minus a half minus 1. Uh, 1 times 2, which is 2. Can we move forward by any chance? I'm going to do it down here then. Plus minus a half, minus 1 over 2. And then we're going to times by x squared, aren't we? Here. But remember, x is minus a quarter x here. That's what it's substituting in for x. It's going to be minus 1 over a quarter x all squared. How many terms did it say? The first... 3 terms. Okay, so that should be it. Okay. Cool. And then we just need to do that. So half lots of, and then we get a 1. And then we're going to add minus a half times minus a quarter. That's going to be an 8 x. And then we have this bit here, so it's going to be the second part. That's going to be minus a half of minus a half minus 1 over 2. But then that's being times by minus a quarter squared, isn't it? So that should be plus 3 over 128x squared. Okay. Cool. If we just simplify the numbers and the fraction bit, well then we could just times the half in. So then a half plus a 16th x, add 3 over 256x squared, and that should be your answer. Cool. Okay. So let's have a look. So then this is very common. Then you have to consider the expansions as to approximate something. Here it's root 2. And you're given some 3 possible substitutions. Then we need to state which of the 3 values should not be used. So if you should not use it, well, it's going to hint about the validity, isn't it? So what you should remember is this bit here. You can only use this expansion when the mod x. So here, mod x is minus a quarter x here, isn't it? That has to be less than 1. Therefore, well then that's going to be just become a quarter x, because obviously with a modulus, a negative becomes a positive. And then we could just times by 4, so then x is going to be less than 4. And then that obviously means the modulus of x, so it could be plus or minus, as long as it's between 4 in size. So this is a minus 4 less than x less than 4, okay? Okay, but let's have a look then. Which of the values do we got? Well, we got x is minus 14 here. That is outside of 4, or minus 4, whatever. So do not use x is minus 14 since well, mod of minus 14 equals 14 is greater than 4, so it's not valid. I should say specifically, the expansion is not valid. Is not valid. Okay, cool. And then part II, a very interesting question. The second part. Alright, slowing down now. The second part is saying, which of the 3 values we give them as accurate or the best approximation? So this is not valid, so it's between these two, but both of these are valid because they're between 4. So which one to give the best one? And the answer will be, if it comes up, always be the one that's closest to 0. Okay, so minus a half is closest to 0. As obviously mod of minus a half is less than mod 2. Okay, so that's closer to 0. So would give the better approximation. But quickly, why is that? But that's because again we are adding, but essentially this is like a polynomial right? Expansion. So we have 1 plus some lots of x, that's sum over lots of x squared and blah blah blah. But the coefficient doesn't matter. So it's like 1 plus x squared. Now, essentially, obviously, it becomes more valid, the expansion, when we add more terms. But say if we're limited to, like, for example, only the first 3 terms, uh, actually, if we had a smaller value of x, say 0.001, compared to, say, 0.99, say we did that to the 5 and this to the 5, that would actually give you a smaller, that would get you closer to 0 than this would. As an example, 0.001 to the 5 is actually 10 to the minus 15. Very, very small number. And 0.99 to the 5 is 0.95, roughly. So that's still fairly significant, isn't it? But this is pretty close to 0. And that's going to happen. So that's telling you, actually, if you, because the powers are close to 0, are pretty converge closer to 0, then actually we need less terms to get an accurate answer. Or we could overall say, well, if we added higher powers of a small number, they become quite insignificant. Say if we added 10 to the minus 15, that's very insignificant. But if we added 0.95, that's way more significant and impactful. So for higher powers of x, a smaller x will basically get rid of. It will go to 0. So only the first few terms matter. Therefore, a closer value of x to 0 will give a better approximation. Okay, cool. Question 18, again harmonic, Ferris wheel type questions. Have a look at it. Again, part A, pretty common. Express 10 cos theta minus 3 sin theta in this form. So it has to look like r cos theta plus alpha. Now, there is, I guess, a shortcut. So you could say r is the square root of 10 and 3. Then alpha is inverse tan of 3 over 10. But let's go over the methodology. And actually, in this question, actually, it is better to do the full thing. And I'll show you why in part B. But we're also given the trig identities. So you don't need to know the addition formula for cos. It's given here. So let's substitute it in. So cos A plus B, well, it's times by r. So it's going to be r of cos theta alpha. That's going to be cos theta cos alpha minus sine theta sine alpha, right? That's just from the formula book. If you do not remember it, hopefully you might be able to go. That just goes to r cos theta cos alpha minus r sine theta sine alpha. Okay, cool. Now it's like with like partial fractions when you compare and stuff like that. You can compare the coefficients here as well. So the cos theta term, cos theta, wow, the coefficient is 10. Well, therefore, that's telling you that our cos alpha has to be 10. And also minus 3 sine theta. Sine theta is here, so that means r minus r sine alpha has to be minus 3. But then, obviously, you can divide the negatives to say r sine alpha is 3. And we've got 2 equations. We can solve them, right? Well, the best way to solve this is firstly recognise if we square both of them and add them, well, that's going to be r squared cos squared alpha, add r squared sine squared alpha. Well, that's going to be 10 squared, which is 100, add 3 squared, which is 9. So that'd be 109. Okay, and what's good about this? Well, we can factorize it to cos squared alpha add sine squared alpha, 209. But then this will go to 1, wouldn't it? Because of the identity, cos squared theta and sine squared theta is 1. So therefore, simply r squared is 109. So then r is root 109. And it's positive. Right, it says it here, but usually the assumption is it's always positive anyway. But there we are. Okay, then we found r. Now how are we going to find alpha? Again, you could either just substitute r in and then inverse cos, or inverse sine to solve alpha. Or, I guess a cleaner way is, notice you can divide the second one by the first one to get r sine alpha over r cos alpha gets you 3/10. Well, the r's are cancel, but we also know sine over cos is tan alpha is 3/10. And there alpha is going to be inverse tan of 3/10. And that's going to be how many decimal places does it say? 2. Okay. So inverse tan of 3/10. Oh, hang on, it's in decimals. It's in degrees, isn't it? Yes, I'm in radians. Make sure you check convert to degrees now. You get this number here. 16.699, blah, blah, blah. Which two decimal places is going to be 69 will round up to, that would be 7, right? Degrees to do TP. Cool. So therefore, bring it all together. What was it? 10 cos theta minus 3 sine theta. It's going to be root 109 cos of theta plus 16.7 for alpha, right? Hopefully copied that down right, yes. And there we go, cool. And again, like I said, alternatively, again, you could just, if you're proficient, you could just recognize r is going to be the square root of the squares of the coefficients. Kind of like Pythagoras, right? The distance between 10 and 3. And then tan alpha you can find by saying tan alpha is 3/10 by immediately dividing the second coefficient by the first. So then 3/10. But I'm going to show why it's more useful to do this approach because part B, let's have a look at part B. So part B is the actual modelling bit now. So that's quite common. Part A is going to be harmonic like this. And then part B, you get into the modelling. We're given the height above ground, h meters, pay attention to the units, and t minutes. Pay attention to the units. And we're modelled by this, but A is a constant. And we've got 2 cycles. We can see that on the graph. And the initial height is 1 meter. So that's saying when obviously t is 0, h is 1. First of all, we need to find a complete equation. That means we need to find any missing values. So here it's A. Okay. Okay. So I'm going to reiterate what h was. So h was A. Was it minus 10 cos t? No, it was like 70, 80 t, wasn't it? I can't remember. 10 cos 80 t. There we go. Add 3 sine 80 t. Okay, but I recognise this is quite loosely, well, not loosely, but I can recognise this is in this sort of form here. But all I've done was say this is minus. I can factor a minus out, say it's 10 cos 80t minus 3 sine 80t, right? And now this is identical to this in part A. So then I can substitute it in to say that h is going to be A minus root 109 cos. Now theta is 80t now plus 16.7 degrees. There we go. Cool. Oh, the A looks like a 9 here. And that's 109. Okay, cool. But we got this condition here. Also, we were given when t is 0, remember h is 1. So we need to use it to find A. Well, then, therefore, we substitute it in, and we're going to say 1 is A minus root 109 cos of, well, it would just be 16.7 degrees, right, for t. Now, that won't give us, now actually, notice, it doesn't say to round A to anything, so it kind of implies A has to be some sort of exact number. But if we did all of this, that would give us a decimal, wouldn't it? That would have been nice. That's where I say the workings in part A are going to help, because this is essentially r cos alpha, isn't it? Let's have a look at our working. Look at one of these two equations. This is r cos alpha, which is 10. So we can substitute it in directly. Because then we can say that 1 is a minus 10. And then therefore a is just going to be 11. And that's an exact number now, right? With no decimals or anything like that. So now that the complete equation, it's going to be h is 11 minus root 109 cos of 80t add 16.7 degrees. That's all in degrees, sorry. And that's our complete model. So remember, when it says complete model, I keep reiterating this, but once you found the missing values, you need to restate the formula with all the values, okay? Or else you'll lose a mark. Then it says, oh, that's only 2 marks. And then for part 2, then you need to find the maximum height. So then max h, or the maximum height, that's going to happen when? Again, look at this. So now this is our h function. Well, you're going to need to recognize what the cos, right? The cos graph. So cos of any angle is going to be between 1 and minus 1. So therefore the maximum is going to be 1 and the minimum is minus 1. But we are subtracting by cos. So therefore to get the maximum, it's going to be making cos minus 1, isn't it? Because then minus and minus will give positive. So it's going to occur when cos of 80t plus 16.7 degrees equals minus 1. And so therefore h is going to be 11 minus root 109 of minus 1. So it's going to be 11 add root 109. Okay. And yeah, that's it really. It doesn't say leave it, don't round it to anything, so just leave it as exact like that. And that's the maximum height, right? Then it says for part C now, I'm probably have to make more room here. Okay. And what's part C saying? From the time taken for the passenger to reach the maximum height on the second cycle. Okay. So obviously like here, look at the graph here. This is the maximum height of the first one. Obviously, we work that out to be what's that weird circle, isn't it? It's like 11 add root 109. But we want this. We want the time at the second one. Well, so firstly, well, remember the maximum height occurs when cos x of cos 80t, sorry, that's 16.7 equals 1 minus 1, right? That's when the maximum occurs. That's what we're solving from the time of maximum height here, right? Well, then therefore, 80t add 16.7. We're going to solve with cos of minus 1. So it's going to look like this, right? So minus 1 is down here. So it's going to be exactly here. So it's going to be pi. And then the next solution is going to be pi and then another 2 pi. So it's going to be 3 pi. And that should correspond. But it's in degrees, isn't it? So it's going to be 180. So it's 180, then 3 lots of 180. So it's going to be 540. Isn't it 180 times 3? Oh, no, 180 add 360, sorry. You're adding 360, not times it by. Sorry, but that's the same thing in this case. 180 add 360 is 540. Okay, so that's the second positive solution, I hope. I forgot God's sake, won't let me get rid of this now. I'll leave it. Oh, is my thingy frozen? Have a look. Let me check the stream. I think it might be frozen. It doesn't look frozen, but it's not letting me. Oh, there we go. Now it will let me do it. Okay, fuck, bloody hell. Okay, so that's the second one. So it's going to be corresponds to this one, isn't it? For the second height. Anyway, so therefore solving for t, where we're going to subtract 16.7 to both sides. So 180 take away 67. Well, it's going to be 113, and then 540 take away 16.7 is going to be 523.3. Oh, hang on, that's not right. 180 to 113. I must have put that in wrong. 180 take away 16.7 is going to be, there we go, 163.3. What's going on now? There we go. Nice, it crashed. Let's try it again then. And probably I'm going to have to speed this up a little bit though now. I would say, oh, I've got to do it all again. Okay, but not much was lost. So firstly, 180 take away 6, that's going to be 163.3, and then the next one was 540 take away 16.7 was 523.3. Like I said, this is the second positive one, so we're interested in this. So that's 80t now by subtracting 16.7. Therefore, t is going to be 523 divided 0.3, sorry. Oh my god. Divided by 80. And so that's going to get me 6.54125. What's it? That should be the time it reaches the second one. To the nearest second. Okay, so now we have to pay attention to the units. So, notice I underline the units, and this is why I underline them. H is in meters and T is in minutes. So this is in minutes. We need to convert this into the nearest second. Well, the best way to split this up is, say, 6 mins and 0.41542125 blah 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 mins. So that's fine, that's in minutes, but we need to deal with the decimal component. The best way, because it looks extremely nasty, how am I going to get this to seconds to round it or whatever? The best way is to say, well, we know that 1 minute is 60 seconds, don't we? Therefore, we can then say 0.54 blah 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 mins is going to be 60 times our 0.54 blah blah blah. So just times by 60 to get it to the nearest in seconds. And actually, we get this number here, 32.475 secs. Okay. So therefore, that's saying that the overall time t is 6 mins and 32.47 sec. Oh, that's awful writing, even for my standards. 6 mins and 32.475 seconds, right? But we need that to the nearest second. So that's going to be equal to 6 mins, and then 32.4 will round to just 32. So that's 32 seconds to the nearest second. And that's the sort of strategy if you have a really weird sort of like conversion. Just do it like that. Okay, there we go. Cool. Okay, let's have a look at part D then. It's decided that to increase profits, the speed of the wheel is to be increased. So essentially, the speed of the wheel, you're going to get more cycles, right, per time. So it's going to instead, the way the waves are going to like squash closer together to show more rotations. So it's going to look like this, isn't it? Although not exactly like that. But they're going to be more compressed. There's going to be more waves, right? Let me see if we can draw it a bit better. Something like that, maybe. But essentially, the that's being compressed. The waves are being compressed, right? How do we compress a function like this? Well, the y value isn't going to change. It's going to affect the x. So the x coordinates essentially going to be squeezed down. Well, if we want to squeeze something, we times by a number. So if we have f of x, then f of ax, that's going to divide every x coordinate by 1 over a, isn't it? So if you times by a number in the function, the transformation is you're going to divide by a, so that's going to squash the graph by a factor of a. Okay, so it's going to get closer together, squashed down by a factor of a. So we need to introduce essentially a number in h of x or h of t to like h of 80 or something like that, or bt or whatever. Okay, this factor b to squash the graph closer together to get more revolutions quicker. Okay, but how are we going to do that? Well, we already have an 80t, so it's already been squashed the cos graph by 80. So we're going to need to increase it essentially to like higher than 80, right? To squash, to compress the waves closer together, to get more revolutions. So therefore, we're just going to say something like, I don't know where to say it actually. There's no room. I'll say it up here. There we are. Got more room. Part D. We need to essentially increase the coefficient, right? The coefficient of t uh, to higher than 80. Okay. And I guess you could say to not stretch, but what's the opposite? Not stretch, you're sort of compressing, right? To compress the graph, to compress uh, the graph, to compress the graph more, right? You know, the sort of compressing where the waves will be closer together. Okay, cool. Question 9. So we're given that in t seconds. The pendulum takes one complete swing like this. So that relationship can be written like this. So this is very common. You'd want to do this anyway with some sort of log modeling to take logs. But let's have a look. So we need to take logs of 10. Okay. So we have t, so part A, t is a l to the b. So then log 10t, first of all, is going to be log 10 of a l to the b. Then we can split this up to say, well, because we have a product, this is going to be log 10 of a add log 10 of l to the b. And then we can then bring the b to the front and then say it's log 10 of a add b log 10 of l. And that's exactly what we've got here. And there we are, nice 2 marks. Okay, now we've got the modelling bit. So we've got this graph of log 10 to the t of log 10 to the l, not t and l, but log 10 of them. Okay, bear that in mind. A student carried out an experiment to find the values of a and b, which are obviously unknown, and they they've given this graph, and we got 2 points right in the log the graph. And actually, there's well, essentially simultaneous equations because we've got 2 points and 2 unknowns. But you could recognize this vaguely looks like y is equal to m is b, mx plus c. Then you could recognize we have between 2 points, the gradient would be this b value, and then c would be then you could substitute a point in to find c. But really, you could just do simultaneous equations essentially, because if say we're going to let's firstly sub minus 0.70. So that minus 0.7 is going to be log 10L, and 0 is going to be log 10 of t. Okay. Hopefully, because that's sort of like the y-axis, and that's sort of the x. So the x and the y coordinate follow like that. So I'm going to substitute it because it's log. So I'm going to substitute it into this equation that we found in part A. So then log 10 of t is going to go to 0. And then log 10 of L is going to be minus 0.7. And that's going to be B, and then add this log 10 of A, okay? Also, then we can sub the other point in, 0.21, 0.45. And so then log 10 of T is going to be 0.45. And then log 10 of L is going to be 0.21, okay? So then 0.21b as log 10a, and that's the second equation. Now we can solve them. Obviously, we've got a log here, but it's still just a number, it's a constant. So to solve this, really, you can then subtract one from the other. So let's subtract 2 from 1, because then that'll get rid of the log 10a, wouldn't it? So then that's going to give 0.21b minus 0.7. So we'll be adding 0.7. So that's going to be 0.21 add 0.7b, which is 0.91b. And that's going to be 0.45, okay? But then that's the equation for b. So then b is going to be 0.45 divided by 0.91. So then that's going to be 45 over 91. Cool. And then log this simultaneous equation. How are we going to find the other one, the log 10a? We're going to substitute it in. Let's sub it into the first one, because there's a 0 here. So then we could say minus 0.7 lots of 45 over 91. Add log 10a is going to equal 0. Then that means log 10 of a is going to be, well, 0.7 times 55 over 91. If we move it to the other side, so that's actually going to be 9 over 26. If you times 0.7 by 45 over 91. But then a, again, you could then raise to a power 10 on both, well, not power 10, but 10 you can raise that by 10. Does that make sense? So a then is going to be 10 to the 9 over 26. And yeah, that would get us as a decimal, if it matters. Oh, it asks us to round both of them to 3 significant figures. Oh, okay, so yeah, we're going to need to get the decimal of this. So 10 to the 9 over 26 is going to get me 2.2189, blah, 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 up to 3 significant figures is going to be 2.22 to 3 sig figs. Okay, and I'm going to need to do the same for B. So that's going to be 45 over 91. That's going to be 0.4945. Now 0 is insignificant, and there's no significant digits before it. So the first significant figure is going to be 4, then 9 and 4, and then we have a 5, so that around to 0.495. 236. So then the complete model, again, a complete equation of this, we need to rewrite it then. It's going to be T is A, which is going to be 2.22 L to the 0.495. There we go. And then part C, with reference to the model, interpret the value of the constant A. Okay. Well, with these sorts of interpret questions, usually you kind of have to consider setting the other parts to 0, something like that. So it's either going to be some sort of y-intercept, initial value, or a gradient. But here, if I notice A is bundled with L to the B, if I make L is 1, then I'm left with T is A. So actually, so then what's T and L? What is T and L? I've never actually saw this yet. T is time for a pendulum to complete one swing, and L is meters of the pendulum. Okay, so then A is going to correspond to T is the time for one complete. So A is going to be the time to complete one full swing. Pendulum, but specifically when L has to be 1. Obviously, you can't set L to the 0 because B's a constant. We worked out B already. So the only way to get the other part to 1 is to set L to 1. Okay. Well, L1, remember L corresponds to the length of the pendulum. So that means a pendulum which has a length of 1. And that's in meters, I believe. And yes, that's the sort of interpret question. So you just got to basically, for that sort of question, you got to realise what each variable is representing, what T and L is saying, right? What all those mean, and then you can kind of just isolate to A on its own. How are we going to get A on its own? Right? Set L to 1. Then what does L to 1 mean? Well, it's a length of 1, and therefore T. You know what I mean? Then T is A, so that means A has to be T. So A is the time, specifically when the length is 1. Something like that. Okay. Quite not the nicest one though, I will say, but yeah. Interpret means you've got to basically explain what they all mean in the context of the question. Okay, question 10. Figure 1 is a graph showing the trajectory. Okay, this is all waffle. Well, not waffle, but I'm just going to read the question. Find a quadratic equation linking h to x. So h is the height of the ball, and the horizontal distance is x. Okay, that's what I get from this. And then we give him some details. The ball reaches a maximum height of 12, and hits the ground of 0.40 meters when it's kicked. Okay, I'll bear that in mind. So first of all, quadratic equation, a general quadratic equation, a good strategy is just to say, well, h of x in general has to look like ax squared plus bx plus c. Okay. Now let's consider some points. So, well, firstly, I notice it goes through the origin, which is 0, 0. Um, so let's substitute. So then that means h is 0, x is 0. So therefore, substitute that in 0 is going to be, well, a of 0 plus b of 0 plus c, well, therefore c is 0. So therefore, our equation is going to be h is simply ax squared of bx. I made that capital. I don't know why I made a capital, but nothing else. There we go. So ax squared plus bx. Cool. Now we are also given it reaches a maximum height of 12. Here we don't know what the x value is, and it also hits the ground, which is going to be here at 40. So 40 is going to be x here. So actually, we know another condition. So we know that when h is 40, no, sorry, h is 0 because it's on the x-axis. X is 40. Therefore, 0 is going to be 40 a lots of 40 squared, add b lots of 40. Therefore, we could say, I think that's going to be 1,600, right? Yes. A add 40b is equal to 0. Now we got one equation. Cool. We need another one. Okay, so let's have a look. We're given the maximum height is 12. Now, actually, one thing you could do is complete the square on this, and that wouldn't be too bad because it's just this. So you could say h is a lots of x plus b over. Well, first of all, we have to factor an a out, so it's going to be a lots of x squared and b over ax, right? And then we can complete the square on this bit. So then it's going to be a lots of x plus b over 2a because we halve the x coefficient squared, and it's going to be minus b squared over 4a squared. And then the y value has to be 12 for h. H is 12. At the maximum, this will go to 0. So therefore, you're left with this bit having to equal 12. However, it's quite nasty. So what you could instead do, well, is how else could I approach it? You could differentiate, but again, you're going to get a nasty sort of a expression like that. Because then what dh dx is going to be 2a add b equals 0. Well, x is just minus b over 2a. Kind of like the turning point, right? But then you're going to substitute it back in and you've got to square it and do it's a whole mess. So we need to come up with a better way of solving it. And actually, realizing this particular instance, we have the two roots, don't we? 0 and 40. What do we know about quadratic? Well, it's always symmetric, a line of symmetry in the middle of the two roots. What's in the middle of the two roots? 40, 0. 20, right? Because then that's going to be 20, and that's going to be 20, because overall it's going to be 40, right? So you could realise that. I think that's the best way to do it without getting a nasty sort of equation solver. Not equation solver, a nasty way of solving. So we get 20. But then that's another condition then, because we have another exact point. We can then say h is 12 and x is 20. So therefore 12 is then going to be a lots of 20 squared and b lots of 20. Therefore, that's probably going to be 400, right? 20 squared, 400. A add 20b is going to equal 12, and that's equation 1 again. That's equation 2. Lots of simultaneous equations so far. We need to make more room. Okay, cool. So, we need to solve this. Again, for 3 marks, you probably could just put it into a simultaneous equation solver, but if you want to cover your back, well, I can immediately say in spot that if I double the second one, I get 800A, add 40B is 24. Then if I subtract this one, then if I subtract that by the first one by 1600A, add 40B equals 0. Well, then 800 minus 1006 is going to be minus 800A, and then the 40B is cancelled, then left with 24. Therefore, A is going to be minus 24 over 800, which is going to be minus 3 over 100. And it makes sense it's a negative because look at the shape of the quadratic, it's a frowny sort of shape. So that means it has to be a negative coefficient of x squared. Cool. Then we could just find b then by substituting it in. So, for example, let's substitute it into the first one. So I'm going to say sub into the first equation for a. Remember the first equation is here. So then that's going to tell us 1,600 lots of a, which is minus 3 over 100. Add 20b, was it? Equals 0. Yeah. No, 40b is 0. Here we go. So therefore 40b then is going to be well, 1,600 times by 3 over 100 gets me 48. Okay. So that's going to be 48. So then b is going to be 48 over 40, which is 6 over 5. Lovely. So therefore then, go back to part A then. At the end, oh, again, we need to write the equation at the end. So h then is going to be a, which is minus 3 over 100 x squared, add 6 over 5x. And there we go. Cool. Then it says the ball passes over the horizontal bar of a set of rugby posts that's perpendicular to the path. The bar is 3 meters above the ground. So it's going to be, well, this is height of 12. So 3 is going to be a lot about here, isn't it? Or here. Okay. But the furthest away is going to be this one here. But anyway, this is going to be at h is 3. We need to find this value of x here, right? But how are we going to solve that? Well, we're just going to plug h is 3 into our model, aren't we? So then h is 3 to get the horizontal distance, which is x. So then h is 3, we're going to get minus 3 over 100 x squared, and 6 over 5x is 3. Therefore, minus 3 over 100 x squared, add 6 over 5x is minus 3 equals 0. And then we need to solve for x. Now this is a quadratic, but again, if you're a bit unsure about putting a quadratic solver, most smart schemes might be okay with it, but you never know. The odd one where they expect you to show how you solve it. Again, just jot down the quadratic formula quickly. So then x is going to be minus 6 over 5 plus or minus the square root of 6 over 5 squared minus 4 lots of minus 3 over 100 minus 3 over 2 lots of minus 3 over 100. And then instead of, obviously there's a lot of stuff you're putting in, don't put that into the calculator, just then put it into the quadratic solver. So then you're going to get minus 3 divided by 100, that's minus 0.03, and then 6 divided by 5, that's 1.2, and you get minus 3. Did it say to round it? Because I'm getting a weird number here. I'm getting a decimal, but it's not asking me to. Although I do have an exact number, I guess. Let me check my workings. Anyway, so we get. So what I get is essentially 20 plus or minus 10 root 3. And so that's going to be 37.32, blah, 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 or 2.679, blah, 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 in meters. Well, that makes sense, actually, because obviously, like I said, there's going to be two valid solutions, right? Because h is 3, it's going to be here, but then if we continue it on, you're going to hit the curve over here. about like 3 point something. So I guess we just round it, I guess. I don't know. Or just give the exact value. So therefore, greatest distance, horizontal distance, is going to be the bigger value, isn't it? That's going to be equal to 20 plus 10 root 3 meters. And that's really it, essentially. Then part C, very classic. Give one limitation. I'll do it up here. And the one you can be right most of the time, well, all the time, when really. Unless there was one example when they said excluding air resistance, give another limitation. But the one you could say is the classic air resistance, right? Um, effect of wind, not on wind, of wind, not not included in the model. Okay. Um, uh, but I know if they do say that and you can't use that, the other one you could use is to talk about how the ground would not be perfectly flat. This horizontal ground here, which should also be fair, pretty much the same for most of these models. Um, because even if because the ground is going to be like very slightly hilly, right? The ground cannot be perfectly flat at 0 degrees. It might be like 0.15 degrees perhaps, something like that, but it's not going to be perfectly flat, and that will affect like stuff like where the graph crosses the grass, not the grass, sorry, the ground, where the height would free be and stuff like that, you know. So it would affect the model. But let me just check my answer to this. I'm not entirely sure. Yeah, so bear in mind, this came from 2018 paper 2. Yeah, okay, that's fine. Yeah, that is the right answer. 37, 20 plus 10 root 3. They gave the rounding of 37.3. I just thought it was weird because it didn't ask for like rounded to like the nearest meter or something like that. So I thought it'd be a nicer answer than that. But there we are. Okay, cool. Okay, now let's do the other set of questions. Hopefully now, because I split it up into two, hopefully it should be the laptop should be a bit better to deal with it now. Okay, question 11. Now we've got a different first principles question. That will come up. What first principles are going to ask on? We don't know, but let's just assume it's going to be this trig one, which is the harder one. So we want to prove that derivative of cos theta is minus sine. We know that's true, but we need to use first principles. Okay, well, I'm giving the formula for first principles is in the formula book. But this is f dash of x. So let's just call the function cos x, or well, not f of x, f of theta, be cos theta. Therefore, f dash of theta, the derivative. If we use this uh, um, definition in the book, formula book, that's going to be the lim as h goes to 0 of f of theta plus h minus f of theta over h, replacing x with theta. Although I don't think it matters really, but yeah. And then I can just use a function, right, and substitute theta plus h in. So that's going to be cos of theta plus h minus cos theta over h. Now, it's given us some hints, so we can use the addition formula for cos. We are going to need that because we have addition at theta plus h. And again, I quoted it here. So if I do that, it's going to be lim as h tends to 0 of cos theta cos h minus sine theta sine h minus another cos theta over all over h. Okay, what do I do now? Well, then this bit's going to help as well. Oh, these results given to us here, and they should give you it. But yeah. So we're going to use that to guide us. So, well, firstly, let's kind of factorize. So let's get first of all, let's get the cos theta on one side. So that's going to be cos theta of cos h minus 1 over h. And then we can split the limit up again to lim of h tends to 0 of then then minus sine theta, which should be sine h over h. Okay, and now actually notice how now we got these two expressions here, cos h minus 1 and sine h. That's great. But actually, what we can then do is because theta on its own that's not affected by h, so we can just bring it outside and then say cos theta lim as h tends to 0 of cos of h minus 1 over h. Doesn't really matter if you bring it out, you just need to substitute cos h minus 1 over h in, which we'll do in a second. And then I can say minus sine theta of lim h tends to 0 of sine h over h. And now I can directly substitute these two results in, which are given. H tends to 0, that's what's going on. So I can use these two results here. So firstly, cos h minus 1 over h, it goes to 0. So that's going to be cos theta times 0 minus sine theta. Oh, and then sine h over h goes to 1, remember? That was given as well. And that's going to be as h tends to 0. Make sure you write that down. So therefore, that becomes, well, cos theta times 0 is 0. Then minus sine theta of 1 is just minus sine theta. So therefore, the derivative of cos theta is minus sine theta. Good. Okay, make sure you just know that sort of like proof, if you will. But hopefully it shouldn't be too bad. But yeah, it's the same sort of thing every time in first principles. Okay, cool. Question 12. Okay, given this expression here, show that dy dx is this. Hopefully you recognize this is going to be a quotient rule because we have two different functions of x. I've quoted the quotient rule from the formula book here, and it looked like this. So you don't have to remember it, although you're going to have to be able to use it in this form. Well, I can then just say, well, clearly I can say the numerator function f of x is going to be x minus 4, and the bottom function is going to be g of x is 2 plus root x. Okay, but then I'm going to need the derivative, right, in order to use it. So derivative of x minus 4 is just 1, and the derivative of g of x. Well, 2 goes away, but then root x, well, we could say root x is going to be 2 plus x to a half. Therefore, g dash of x is going to be half x to the minus a half. Okay. Okay. Let's go for it. So therefore, then the dy dx then we're going to substitute these in. So f dash of x is going to be 1, and then of g of x, which is going to be 2 plus x to the half. Then I'm going to minus f of x, which is x minus 4, of g dash of x, which is a half x to the minus a half. And that's going to be all over 2 plus root x to the squared, right? G of x squared. Okay, let's do some simplification. So first of all, that's going to be 2 plus x to the half minus, and then x, okay, x, well, it's going to be minus a half x to the minus a half of x minus 4. We'll do that expansion in a minute, and then we could do this. So it's going to be 2 plus root x, 2 plus root x. And so this is going to be then 2 plus x to the half, and then minus a half of x to the half, x to the minus a half times x. Well, you're going to add the powers. This is a hidden power of 1, so it's going to be 1 minus a half, which is just going to be x to the half. Okay, and then x to the minus a half times minus 4, which is going to be minus 4x to the minus a half. And so then that's all over. And then we do this expansion on the bottom. It's going to be 4 plus 2 root x plus 2 root x is going to be 4 root x. And then root x times root x is x. So then if we tidy the top bit up a little bit, that's going to be 2 plus x to the half minus a half x to the half, add 2x to the minus a half. And there we go. And then the bottom, well, the bottom, if the top bit's all in index form, I think it's just best to get this root x in index form as well. So that's going to be 4 plus 4x to the half, add x. And actually, I notice I can also simplify the top a bit more because I have 2x to the half terms. So 2 plus x to the half minus a half x, so it's just going to be half x to the half plus 2x to the minus a half over 4 plus 4x to the half plus x. Okay, where do we go now? Because actually, we need to get it to this. That doesn't look nothing like it at the moment. Well, the key thing here, use the question to guide you. We're going to need a root x of something, right? In our answer. Hopefully you can see that, right? Obviously, it's a factor there of a. But let's ignore that. Let's just try and deal with the root x. That means we're going to have to root x. That's going to be then x to the half, isn't it? We're going to need to pull out an x to the half in the bottom, and then hopefully a lot of stuff should cancel in some way. So then let's say 2 plus a half x to the half plus 2x to the minus the half. And then I'm going to force this by factoring out x to the half. But then that's going to be 4. Well, it's going to be 4 then over x to the half, isn't it? Because then if I times by x to the half, that would just go back to 4. But then x to the half is just simply then going to be x to the minus a half, isn't it? And then 4, and then that's just going to be 4, because that's already with x to the half in it. And then this is going to be x to the half, isn't it, as well? Because x x to the half times by x to the half will just give us x. Okay, cool. So what can we do now? So really, then things should cancel with the top and the bottom. Let's compare. So I have 4x to the minus a half. In fact, let me rewrite this. So then I'm going to say 2x to the minus a half, add 2, add a half x to the half of x to the half of 4x to the minus a half, add 4, add x to the half. Hopefully, what can we do now? It should be a bit more clearer. But notice this factor here is the same as this, but this is just doubled. Right, the bottom bit is double of that. How can we deal with that then? Well, we could just pull out a 2, can't we? So we could say that's 2x to the minus a half. I'm going to do that over here actually now. That's going to equal 2x to the minus a half. Add 2, add a half x to the half. And then I'm going to pull a 2 out to match it. So it's going to be 2x to the half of then 2x to the minus a half. Add 2, add a half x to the half. And now they cancel, right? The top bit's exactly the same as this. And then I'm left with 1 over 2 x to the half, which is 1 over 2 root x. And now we got it. That's now in this form, a root x, where a is 2. There we go. It's quite a nasty sort of question, that is. But yeah, that's the sort of idea. So notice what I did there, right? The key thing I did here was notice I needed it in this form. So I kind of forced my way of doing that by then factoring the root x on the bottom. And then I dealt with what I could after that, okay? And yeah, there we are. Oh man, what a rough question that is. Okay. Okay, question 13. Okay. I think there are 8. So like I said, there are a bit more questions than normal. I think there's 18. So we're on question 13 now. We've got this modulus graph. First of all, it's asking us to find P. Now, what you need to realise is, with a modulus graph like this, or in general, when the minimum point, not the minimum point, well, yeah, it is a minimum point in this case, but I guess more specifically, when a modulus graph kind of flips like this, when it flips, like when it changes course like this. So here, obviously, you have one line here, that's fine, and then it changes to this line. It bends, right? When this sort of bending happens, that occurs when the modulus part of x plus 4 has to equal 0. Because then when it's 0, obviously that's the point where it goes from positive to a negative. And obviously, with like a modulus graph in general, like a line, here, say here, then it hits 0, then it's going to hit back up to avoid going negative. Obviously, it's going negative here because we're subtracting 5 afterwards. So it will force the graph to shift down. But in general, when you just got a modulus part, when it just hits, when it equals 0, obviously when y is 0 here, that's when the graph shoots up and bends and changes course. Okay, so when you ever see that in some sort of modulus question, when it bends like that, and it changes course, that's when the modulus part equals not the whole equation, but just the modulus part equals 0. But then we could solve that as well. How's that going to be 0? Well, then x plus 4 has to be 0. So then x has to be minus 4. Well, that's our x coordinate. Then the y coordinate, well, y is 2 lots of x plus 4 minus 5. And that's going to be 2 lots of, well, like I said, this bit is going to be 0, minus 4, 4, and the minus 5. That's going to be minus 5. Therefore, p is going to be minus 4, minus 5. Cool. Then part B says solve the equation. This is fairly typical as well. A different expression for x. 3x plus 40 is the same graph. 2 mod x plus 4 minus 5. So I think the best way is, certainly probably the most efficient way, is to just sketch both parts, right? Because if we plot y is 3x plus 40 and y 2x minus 4 plus 5, those are sort of like two different lines. And then when they intersect, that's our solution. So let's plot this then. 3x plus 40, but we're going to need a frame of reference. What about this line here? Well, if you just get rid of the modulus part in a way, that's going to look like 2x plus 8 minus 5, which is 2x plus 3. So that's telling you the y-intercept is going to be 3 and the gradient is 2. So compare it to this line, the intercept, well, if this is 3, 40 is going to be literally off the page with this scale. I'm going to say it's like here, 40, but that's still not probably going to be right. 40 here, if we just extend the lot axis. Then a gradient 3, it's going to be even steeper than this, because this is gradient 2. 3 is going to look like this. So 40 and it passes through, it's going to be like, oh, I've got a curve there. It's going to look like this, isn't it? And more specifically, there's only going to be one intersection, and it's going to be here on the left part of the line. How are we going to get that? Well, 3x plus 40 is going to cross with this line part here. But that's going to be, notice the gradient is going down. So that means it's not going to be positive x plus 4. It's going to be minus x plus 4 to make the gradient negative, okay? So that means we're going to need the negative component of the modulus part. So it's going to be, well, 2 lots of minus x plus 4. Sorry, 2 lots of minus of x plus 4, but we could just factor the minus out to just say minus 2 lots of x plus 4, minus 5. And then we just solve it. So we can expand it, say minus 2x minus 8 minus 5. So therefore 5x. That's going to be minus 8 minus 5 minus 40. That's going to be minus 53, isn't it? And therefore x then is going to be minus 53 over 5. And that's our solution. Alternatively, And only when you got when there's no other variables involved. Part C has a variable of A. We'll get onto part C in a minute, but only for the purposes of like this sort of question, when you've got an x's and stuff like that, solving like an easy sort of question like this. Alternatively, another way is you could just use an algebraic approach, because you know the solution at the end of the day can only happen from taking plus or minus of the modulus part. So we have two cases, right, because of this. Either 3x plus 40 is going to be two lots of the positive part and then minus 5, and then you solve it like normal. So then 3x plus 40 is going to be 2x plus 8 minus 5. So therefore x then, subtract 2x, and then you're going to have 8 minus 40 minus 5. It's going to get minus 37. But then we need to check as well, because, like I said, it's not. We don't know what part the line is. Is it the minus modulus or the negative modulus part? If we're not doing any graph sketching anyway, but we need to check it by substituting it into the equation. So I'm going to check. So the left hand side, that's going to be 3x plus 40. So it's going to be 3 lots of minus 37 add 40. That's going to get me minus 71. And then the right hand side is going to be 2 lots of minus 37 add 4 add minus 5. So that's going to be, well, minus 37 of 4 is minus 33, but then its modulus, it flips to positive 33. So 2 lots of 33 minus 5 gets us 61. Now, these are not equal, so therefore x cannot be minus 37. And that checking is crucial, okay, to check, because that wouldn't be, it might solve, but that's not what's going on geometrically. So it wouldn't be a solution. And the second case then, we did the positive part. Now let's do the negative. So 3x plus 40 is then going to be minus 2 lots of x plus 4, minus 5. And that will go to minus 2x, minus 8, minus 5. Exactly what we did, right? That's the exact equation we left with. So I immediately know x is going to be minus 53 over 5. And then I'll check. And then the left hand side is going to be 3x plus 40. So it's going to be 3 lots of minus 53 over 5 add 40. And that's going to be and that's going to be 41 over 5. And that's a 3, by the way. There. And then the right hand side, I'll do it down here actually to make more room. The right hand side then is going to be 2 mod of minus 53 over 4, 53 over 5, add 4 minus 5, right? That's the right hand side. 2 lots of mod x plus 4 minus 5. And hopefully that should then equal the left hand side. So then minus 53 over 5 add 4 is minus 33 over 5, but that'll be a positive, right, because it's a modulus. So then we times that by 2, and then minus 5. We indeed get 41 over 5. So these two agree with each other, so that has to be a solution. So therefore, x can be at minus 53 over 5. And those were the only two cases, because there's only one modulus, so we just take the plus or minus of it. And that's the algebraic way. So you solve it systematically by taking the plus version and the minus version of a modulus bracket. But then you need to check, because geometrically, the line here, there's no intersection with the positive part. So you need to check it. And then obviously there's correct solutions. It should be fine. So that's the other way, if you're unsure. But obviously it's a bit longer. The geometric way, you can cut down the cases, okay? And also the geometric will help with more harder questions like part C. Because now, let me get rid of this part now. We are told that a line L has equation y is ax, where a is a constant. Given that the line intersects the modulus graph at least once, find the range of possible values for a. Okay, so this is actually a fairly sort of typical exam question as well, a harder question though. So you're gonna the best of by far the best way is a geometric way. So a of x. So what's that gonna look like? Well, it's gonna be a gradient of a, but it's gonna pass through 0. So for example, for example, the gradient of this line is 2. So if a is 2, it would match. That it'd be parallel. I forgot to say. Now it's moving the graph. Let's revert it. There we are. It would be parallel, right? That's roughly when a is 2. But then, and this is where I'm going to get the line. I'm going to have to use the line here. I know it's going to be absolutely fiddly though. There we go. So it's going to pass through 0, 0. That's going to be a obviously because there's no y-intercept. The y-intercept has to be 0. So really, you could really use your ruler to consider what happens for if you change the steepness of the line, right? So first of all, yeah, let's consider when for God's sake. Oh my God. I hate this bloody thing, man. But I do need to use it though. I'm going the other way. I'm not flipping it this way. Oh, forget it. It seems to only like going one way, which is so annoying. Essentially, I want it to match the gradient of the line, first of all. Okay, look, perhaps something like the. Oh, no, that's still. There we go, something like that, right? So now we have it parallel. If the gradient then of the line of a of x when a is 2, that is going to be parallel to the line, okay? Because it has the same gradient of 2 here. But what does that mean? If it's parallel, well, then the line's not going to intersect, okay? So that means actually, then if we increase the gradient to make it steeper, even just by a little bit, it's not going to go the way I think it's going to go. Say if we increase it, I don't know, just like 2.2, I don't know how it's not going to work. I know it's not going to work the way I think it is. Yep, it's going to go the other way. I don't want it to go that way. Bloody thing, man. Oh, now it's zooming. Oh, for God's sake. Oh, how bloody annoying. Let's zoom this out. No, that was my fault. That was. Zoom, view. There we go. Go back to 100. Oh my God. It only goes what? It can go both ways. I am trying to move it the anti-clockwise. See, it just goes one way no matter where I scroll it though. Okay, I'm gonna leave it there for now. But imagine A is 2. If we even shifted it even a little bit steeper, so say if we moved it to like 2.2, again it would pass through hit the center, but then it would kind of look. Oh, that's a bit rubbish. Then it would kind of look like this, and it would pass through the right part of the graph. So there would be at least one solution, and that makes sense, right? Because if we're changing the gradient away from 2, the lines are no longer going to be parallel. So that means they have to have a intersection. Any two lines that are not parallel will always have a solution at least once, right? Um, Always, no matter if you could change it by like 0.1 to 2.01, it would then have a intersection because they're no longer parallel. Okay, two lines only don't really intersect are parallel in general, right? Mostly, that I can think of. Yeah, because that's the whole definition, right? Parallel lines don't intersect, so they have the same gradient. So if we change it away from 2, it then is going to have a solution. And therefore, as we're doing here, even if it's just a little bit, uh, so we made it a little bit steeper like this. Although it's not like a line, is it? It's going to pass through at some point, right, on the right side line. So therefore, a is greater than 2. It's going to give a solution greater than 1. Then what about when a is less than 2? What happens then? Well, then let's try and match it again, because this is going to be crucial. Okay, try and get it to match this again. There we go, something like that, right? That's sort of the same line. Then if we made it less steeper, um, well, then it's like this, right? It's not still not going to be a solution. Um, obviously, despite the gradients being different, because that's going to be steeper, so it's always going to be further on the right side. Oh, it's not letting me draw it now. So on the right side of this modulus here, it's too close to the line. It won't let me edit it. So if we continued it there, that's this other line, this AX line now. If A is less than 2, the modulus line here is going to be steeper uh, than AX, the line AX. So therefore, it's always going to be above the line AX, so they won't intersect on the right side. On the left side, if we were to continue the graph, like I said, if the gradients are different, they would intersect because then eventually, because the modulus, say, so let me draw it. This is quite bad. I do apologise for the explanation, but it's just this line. This ruler's not working the way I want it to. If we then continue this line, let me just move it. Actually, there we go. That might make it better. What I was saying then is, great. If we made A less than 2, so then the gradient would be I've got rid of the line now. Say then if we made it steeper, like shallower, like the grade is shallower, like that, but it still wouldn't intersect here, right? But then the line, as we just saw, say like here, obviously then the modulus line here is always going to be steeper than this line because it has a higher gradient. So it won't intersect on the right, okay? The distance would actually widen, as you can see here. So there's no intersection on the right hand side when A is less than 2, okay? A is greater than 2, like we discussed. That'll be A2 match the gradient. A greater than 2 would be steeper, so it would eventually then intersect with the right hand side. When it's less than 2, or actually we need to do some more investigation. Like I said, and also what I said was, if it was less than 2, if we then were to continue, oh, my God, not even the laptop telling me to shut up now. There we go. It's gone back. If we were to say continue this this line forward down here, right? Oh, that's not here. If it was shallower, say here, right, this AX line, then eventually it would cross down here, right? But we're not continuing the line. We're actually cutting it off at this point P. So this is y2, remember. Now, if we keep rotating it, say a little bit, it's still not going to intersect, right? But it's getting closer. It's getting closer, isn't it? Uh, but then, say we rotate it a little bit more, so we make the gradient more shallower. Eventually, it will cross the left part of the V shape, right? The left part of the graph, right? There we go. It starts to touch it. And specifically, it's gonna intersect then this AX, right? If we make A smaller than 2, smaller and smaller, eventually, like we saw, it's gonna pass here, isn't it? It's eventually, if it pass through the origin, um, eventually, it's gonna pass through here, isn't it? It's gonna pass through the minimum point, this vertex point P, and then anything after that. Let's go back again. Anything after that, it's then gonna make it more shallower and then make it negative. Then it's gonna have two intersections, right? It's gonna intersect, say, like this part here and this part here. So actually, what we then need to do is find the gradient when the line between 0, 0 and P are the same, right? So we need to find the line connecting 0 and P. Then we find the gradient, and then anything less than that gradient of A, which is A, will then give us one or more solutions. Hopefully, that made some sort of sense. I want it to be a little bit better than it was. Uh, so then we need to solve, as we discussed, the point where that line that passes through the origin, that line AX, right, then also passes through this minimum point P. So then, y is AX? AX is going to equal to well, we know the point now, so we don't need to solve it. We know it passes through P, which was -4 -5, because obviously it's the vertex. Remember, you just set the modulus part to 0. Then we do substitute it into y AX to get A. So therefore, -5 is going to be -4A. Therefore, A is going to be at 5/4. So so when the gradient is 5/4, that corresponds to when the line AX then would then cross through P. And then anything less than 5/4 would then, as you see here, pass through 0, will then pass through the V shape twice, the graph, right? And it will always be like that, okay? And you might think, oh, well, oh, pass through 0. And you might think, well, what about eventually when again, sort of like the parallel gradient, the gradient of the line matches the left line here. But there's still going to be a solution because in order to get there, it's going to have to pass through the right side. So the only time then there is no solution is when when A is 2x, right? Exactly, or in between until it gets to 5/4. And then when it hits 5/4, remember at 5/4 is when it passes through P and 0, so there's still one solution. Because remember, the question asked us, if I can get it now, let me get rid of the ruler. It asked us, oh, yeah, the question's gone now, but it asked us for at least one intersection with the line y is AX with the graph, okay? And as we discussed, that happens when A is greater than 2, exactly. Because if A is equal to 2, remember, it's going to be parallel to the line here, so there will be no intersection. But then if it's greater than 2, then it's always going to be steeper than the right line, so it will eventually overtake and cross through the right line. Okay, so I didn't want to do that. Say for example, that's 2. Oh, that's not 2. So look, that's 2, and then like we made it a little bit steeper. Eventually, it's going to pass through there, right? And that's always going to happen. And then obviously when we make it shallower, like that. Say for example, then we make it less than 2, a little bit like this. Then it's still not going to pass through. And so then we essentially need to rotate, shift it until then it reaches this point P. And then anything after that is going to cut through the graph twice. So when it hits P and then afterwards, when we make the graph the gradient even smaller, that's when it has one solution. Then it will go to 2 solutions. But either way, and that corresponds when A is 5 over 4. So when A is 5 over 4, it hits P. So there is one solution, and then anything less than that, so make it even more shallower, it's going to cross it twice, so there'll still be one solution. So those are our 2 solutions, okay? So A is 2 and A is less than or equal to 5 over 4. But then it also asks, I remember, then it asks to give it set notation. So that's then going to be this sort of wheeled line, A such that A is greater than 2. And the key point of set notation is you can only have one inequality in each bracket, in each set. So we're going to say or, because it could be either or, and it's represented by this U shape. So remember, like with Venn diagrams or probability GCSE or whatever, if we want to represent 2 different inequalities, 2 different sets, we say or U for the union or. Okay, and that's what's going on here. So or A such that A is less than or equal to 5 over 4. Okay, and that's your set notation. Just to say that this means also, by the way, the values of A and the colon means such that, and then such that A is less than 2. Okay, and the U means or. Okay, and then yeah, so that's the key bit. So that's set notation. Cool. Oh my god, I do apologise. That was a bit incoherent. I did. Well, I'd like to say I tried my best. The ruler screwed me over and everything like that. Okay, question 14. I'm going to get rid of this now. But like I said, if we did this sort of algebra version of solving, it'd be very damn difficult to solve when you're trying to find range of values. And that's why doing it graphically is so much better with modulus questions, because then it shows you exactly where the intersections are going to be. If you did it algebraically for part C, it'd be a right nightmare. So yes, that's the thing to keep in mind. The best way to tackle these sort of questions with modulus is if we give you a line, say like y is ax, um, just use your ruler as the line and just keep changing the position of the line such that you get various intersections and see where that happens. Okay, your ruler will be helpful there. Okay, question 14. G of x is this. First of all, we need. Oh yeah, I was going to get rid of this, wasn't I? So first of all, as I said, find g of 5. So that's just your composition, right? That's a composition of functions that's saying g of 5. Okay, and then well, g of 5 is going to be 2 lots of 5, add 5 over 5 minus 3. So that's going to be 15 over 2, right? Yeah, yes. So then g of 5 is going to be g of 15 over 2. So then it's going to be 2 lots of 15 over 2, add 5 over 15 over 2 minus 3. And so that will be 40 over 9, and that should be your answer. Cool. Part B then. State the range of G. Okay, this is quite a nasty question because you kind of just need it for 1 mark only as well. You just need to spot it. But it can be quite tricky to spot it. So actually, there are two ways of spotting the range. Well, not two, but I can spot at least two ways of doing the range. So the possible outputs of g of x. Firstly, with the range in general, you need to consider basically the maximum and the minimum value of x. You can take the minimum and maximum of the domain. Well, here, x has to be between 5, right? But then there's no upper limit. So in a way, you can kind of say x is less than infinity. Very informally, but kind of that, right? So we need to consider what happens when x is 5 and when x becomes large. So when x goes to infinity. But we know when x equals 5, we found it in part A. G of 5 equals 15 over 2. So then we need to consider what happens when g goes to infinity. Because the whole idea, right, it's going to be bounded, right, g of x will be between 5 and then obviously it will go on forever. So say if it's 5 and then it will tend, like kind of like an exponential curve, right? And so the range will be between 5 and the end, like, value, right, when x goes to infinity. That'll be your range, okay? And that's the idea. But this is where it gets tricky. So then what happens when x becomes large? So as x becomes large, so x goes to infinity, if you will. And there are multiple ways of doing this as well. I think for A level, it's not going to be too bad, especially if they don't give you a graph. If you want to work out what, when x goes to infinity, just plug in a very big number for x. So say if I'm going to plug in x is 10 to the minus 15, then substitute g of 10 to the minus 15, see what happens when x is big, okay? And so if I put that into a calculator, 2 over 10 to the minus 15, no, 10 to the 15, sorry. 10 to the minus 15 would be 0, wouldn't it? No, 10 to the 15, there we go. That'll make it a huge power of 10. There we go. So 2 of 10 to the 15 plus 5 over 10 to the 15 minus 3. And you get 2. And the calculator gives you 2. You might perhaps get like 1.9998 something, but it's going towards 2. So what you should notice is it goes towards a certain number. So that's telling me when x goes large towards infinity, g of x goes to 2. So actually, that's our range, really. But there is one other thing we need to check. But you might be that for only one mark, then you probably say, well, but then 15 over 2 is bigger than 2, so it's going to be between 2 of g of x for the range of 15 over 2. Now, it's not going to be equal to 2, because remember, x is sort of like equal to infinity here when g of x is 2, but you can't equal infinity. It'll just tend to 2. So 2 is like our lower bound, but it can't exactly be 2. You know what I mean? Um, so it's going to be less than 2, but 2 kind of gives a bound, right? So it goes towards 2, but will not equal 2. But g of 5 explicitly is 15 over 2, so it can be 15 over 2. We've worked it out. So that is our range here. Now, hopefully, another way you can is without plugging into a calculator, but if you're unsure, you can just plug in a large value and see what happens. You could say alternatively, that actually, if we then divided both sides of the fraction by x, we get 2 plus 5 over x over 1 minus 3 over x, okay? Divided both sides by x. You should know that 1 over x goes to 0 as x goes into infinity, okay? Hopefully you're clear of that. Divide by a large number, you get 0 eventually. So then we can sort of plug this in. So then as x goes to infinity, the g of x will go to 2 plus 0. 5 lots of 0 is still 0 over 1 minus 0, and that will go to 2. Okay, work that fraction out, which is exactly what we got. Okay, when we plugged in a big number, that's the more formal way of doing it. Okay, and a quicker way, I guess. But that only works with a certain amount of fraction, a fraction like this. But you know, if you're in doubt, just plug a big number in. But that's two ways of working out what happens when x gets big, okay, with a fraction like that, if you're unsure. Okay, and the last thing you need to check, this is why this range question is so awful, because actually for only 1 mark, and I'm being really rigorous here, but you have to also consider the fact that if there's any turning points in between 5 and infinity. So like I said with our graph, I'm not going to overcomplicate it. I think for A level, you are fine. Like I said, just remember this sort of methodology of checking out the minimum, maximum value of x, right, and checking what happens at g at those two endpoints, right. So when g is 5, obviously it's equals 15/2, but then there's no upper limit. So what happens when x goes to infinity or gets large? As we've seen, it goes to 2. So those are two sort of limits or bounds. That would be fine for questions like this. I don't think they'd be go any deeper than that. But especially for those who really aim for the A stars, I'll try and remember. I'd hopefully try and make sense of what I'm about to say. But what you also need to consider, as well as the endpoints, say we have 5 for x and obviously goes to infinity. Well, it was 2 here, and then this fraction here, like 15/2, was it? You might then think, wow, it's like an exponential. It's going to then go from 15/2 and then 10 to 2. Actually, that's what happens now in this case, but why? What we need to check for as well is there any turning points in between? So, for example, 15/2 could then dip down like this, and then it still go towards 2 at the end. But then the minimum value wouldn't be 2, but it would occur at these sort of what's it called? These turning points. So what you need to do to be clarity is to kind of show to yourself that it's a decreasing function. So it's going from 15/2 to 2, and it's decreasing, meaning as every x value gets bigger, the graph will constantly go down. So there'll be no turning points. And to show that it's to get your head around that it's decreasing, where's our function here? Um, do, 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 do. There are several ways of doing it. So obviously you could just differentiate and show there's no turning points when x is bigger than 5. That's the long way of doing it. Alternatively, well, like I said, you could recognize this is a top-heavy fraction, right? We can do algebraic division to then say g of x. Then, well, x minus 3 of 2x plus 5. I need to get rid of the 2x, so I'm going to need times by 2. So then that's going to be minus 2 lots of x minus 6, and then that'll go to 0x, and then 5 minus 6 will go to 11. For God's sake. Which is, but if we do algebraic division, we can say that this fraction then becomes, well, the quotient is 2, and the remainder of plus 1 over x minus 3. And now there's only one variable of x, so it's a lot easier to see how x varies, the function, the range varies. Okay, so then, what would happen then as, well, when x is bigger than 5? what would happen when x is bigger than 5 and then increases? Okay, well, 5 minus 3 will go to 2. So then x bigger than 5, this bit is going to go to infinity, isn't it? Because when x gets big, x minus 3 will get big. And then I'm saying 1 divided by a bigger number of x. When I'm dividing a bigger number each time, I get a smaller number as a result. So this 1 over x plus 3, x minus 3, will be smaller as x gets bigger, particularly beyond 5. So then I'm adding a smaller number each time when I increase x. So without fail, as x keeps going up, it increases. Okay, so yeah, so hopefully with that sort of logic, then you can see as x increases, the fraction overall gets smaller. So we added a smaller one as x increases. So the overall output would decrease. So therefore it's a decreasing function, which means as x increases without fail, the whole function increases, the whole function will decrease. So it's decreasing. So strictly then between 5 and infinity, it's going to flatline like this, okay, when x is like 5 here. So there'll be no turning points because obviously if there was a turning point in between, then it would have to increase, which goes against our logic of it generally decreasing. Okay, but that's all that I think that's all like the top A star students. I know range is a tricky topic. But that's being really rigorous about it. In general, I think you'd be okay, like I said, to reiterate, just consider the two endpoints, the two values of x at the extreme. So x is 5, because it said x greater than equals 5. So 5 is the lower bound, right, the lower value, but then it can just go to infinity as the upper. So consider what happens at 5, and then when x gets large, and then that's your range, right? So these are two values. There we go. Okay, part C. Then it's asking for to find the inverse. A nicer question. There we go. So g. So I'm going to say well, y is going to be g of x. So y would be 2x plus 5 over x minus 3. Okay. So then, what happens with inverse in general? Well, the coordinates x, y, right, for g of x, they flip to yx. So kind of like how the input now for g inverse will be y, and then the output's x. So we need to flip the role of x and y, okay? So that means x minus 3 lots of y is going to be 2x plus 5. So then let's expand it. So then xy minus 3x is 2x plus 5. Now we need to rearrange to put x then in terms of y. So let's get all the x's on one side. Oh no, that's minus 3y there. There we go. So then x of y minus 2. Okay, xy minus 2x. It's going to be 3y add 5. Therefore, x then is going to be 3y add 5 over y minus 2. And then we just need to put the x in and say g inverse then of x is 3x plus 5 over x minus 2. Cool. So that's the inverse function. But then it's asking for the domain. And what you should realise is, again, because of the role of x and y switching, the range of g of x will become the domain. But we worked out the range of g of it in part B. So the range of g of x will now be the domain of inverse. So therefore, the domain is going to be 2 less than x less than equals 15 over 2. Cool. Okay. Trying to think. So that's sort of a function question. Not the nicest one, but hopefully, again, this is very similar to the 2022 one. So hopefully, if you see the methodology and sort of the reasoning, hopefully then you'll be in a position to tackle it tomorrow, or hopefully make some sort of sense. So let's stare at it for a little bit more. I'm trying to think if I wanted something else to say. Uh, Trying to think. I don't know. I was gonna say, but pretend. No, I'm not gonna confuse. No, I'm not gonna confuse you. Okay, question 15 then. Oh, a few more questions to go now. I do want to actually wrap this up fairly quickly. It's actually set. I've been on this for ages now. I've done this quite slowly. I was meant to go faster than this. I had a lot of disruption and stuff, though. I do apologise. Anyway, let's. We have this. So we had arithmetic series in paper one. Uh, so likely geometric will come up. We already covered a recurrence one, but I think this will come up as well. Like I said, I did cover another one in my other paper, which I'll link my revision session. But let's go over this one. So we're doing a geometric series, general one, combination R and first term A. And we need to prove it, and you should recognize that's a general summation. So it's asking for the proof, okay? And you do need to remember it. It might come up, in some way. So let's just quickly go over it. So in general, remember a geometric series of UN, right? It's going to be A, then AR, then AR squared, and then dot 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 to AR n minus one. That is the nth term, right, of a geometric sequence. So therefore, the series is going to be adding all the terms. It's going to be add AR, add AR squared, add dot dot dot, add AR to the n minus one. Okay, but how do we go from there to conclude this whole fraction? And actually, I think rearranging this a little bit might help us. Let's then say then 1 minus r lots of Sn is a lots of 1 minus Rn. So then, with that in mind, we'll then now expand to Sn minus Rsn. So then let's consider Sn and then Rsn, right, times by r. So then that's going to be AR, add AR squared, add AR cubed, add AR to the n, right? Because n minus 1, r to the n minus 1 times r to the 1, we'll add them to get n, okay? And then, like we said, we should consider then taking the first one away. So therefore, Sn minus Rsn, and that's going to be a plus AR plus AR squared plus dot 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 plus AR to the n minus 1. And then we're going to minus it with AR minus AR squared minus dot 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 minus AR to the n. So how do we go here then? What can we do here? Well, actually, we can align them together, right? Because notice AR will go here, AR squared will go here, and then AR to the n minus 1 here will go with the left AR n minus 1 there. So we can align it to say A plus AR squared at dot 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 add AR to the n minus 1. And then I'm going to subtract AR here, subtract AR squared, subtract dot dot dot, subtract AR to the n minus 1, and then I have another AR to the n term there. Now, hopefully, you might be able to spot what we can do here then, if we rearrange it, because I notice the terms are basically the same, but I'm shifting by 1. Because AR's the second term here, but it's the first term there. AR squared is the third term, but it's the second term in the second one. So if I could just align the terms together, I can then notice they cancel, because then I have AR minus AR, then I'm going to have AR squared, take away R squared. And by that logic, it's going to continuously cancel out. And then I'm going to have AR to the n minus 1, and that will cancel out here. And so I'm left with A minus AR to the n. So therefore, 1 minus R to the Sn, remember that's the same as Sn minus Rsn by factoring out Sn. That is now A, and then I can factor that out, say A of 1 minus R to the n. And hopefully, that's 1 minus R to the n. Now hopefully, we can see now if we divide by R1 minus R, we're going to get A lots of 1 minus R to the n over 1 minus R. And is that not the formula they wanted? Yes, it was. Cool. There we go. So that's the proof, right, for 4 marks. But then we're told, I think I need a charge. We are then told that S10 is 4 times S5 for some series, right? So that would mean S10 is 4 lots of S5. So then we need to plug n is 10 and n is 5 into this. So therefore, A lots of 1 minus R to the 10 over 1 minus R is equal to 4A lots of 1 minus R to the 5 over 1 minus R. And then we could kind of go from there and solve it. But immediately I noticed the 1 minus R will cancel on both sides, and the A's will as well. Okay, so that I'm left with 1 minus R to the 10 is 4 lots of 1 minus R to the 5. Again, if you're unsure of that, you can just cross multiply. But then you should notice things will cancel if you continue it that way. Okay. But then we're left with this. So then I can say 1 minus R to the 10 equals 4 minus 4R to the 5. Then we're going to rearrange, move everything to the right. I'm going to say R to the 10 minus 4R to the 5 at 3 equals 0. Yes, because 4 minus 1 we get 3. So where do we go from here? Well, hopefully you recognise that this is now going to be a hidden quadratic. If I then say let u is r to the 5, we then get, well, r5 squared is r to the 10, right? So then we're going to get u squared minus 4u add 3 equals 0. And then we can solve this, can't we? And in particular, that's going to factorize to u minus 3, u minus 1, I believe. U squared minus, yeah. So then u is 3, u is 1 is our solution. And then let's reintroduce it back. Therefore, r to the 5 equals 3, or r to the 5 equals equals 1. And then r is going to be the 5th root of 3, or r is the 5th root of 1, which should be 1. And then this we'll get a decimal, but it's asking for the exact value. So that would be a third, right? An exact value. But we've got two solutions, and also bear in mind it's not plus or minus, because only when you have an even root do you plus or minus, because of the fact that minus 1, for example, to the 4 would be positive. So we have to count for plus or minus, but minus 1 to the 5 would still be negative 1. So when you have an odd root, you don't do plus or minus, okay? Just to emphasize that. Okay, but we have two solutions. Let's have a look. It told us here R cannot be 1. So therefore, obviously that rejects that one directly. So we can say, but R cannot be 1. So R is the 5th root of 3. And there we go. Cool. There we are. Question 16. There should be 2 more questions. Yep. 3 more questions, sorry. But a shorter question after this. Okay, question 16. So part A. So I do predict they're going to mix partial fractions with differential equations. A question like this. They haven't actually asked too many questions like this. They've asked one in 2022, but I went over that in my last session. So I wanted to get a different question. So this is the only one, and the other time they've asked a question like this, it's in the samples. So in the last, well, it's coming up to like 5, 6 years now. They've only asked it once officially, really. So they might ask it again. I don't know. Anyway, so part A, we need to express it in partial fractions. This should be fairly bog standard. So that's going to look like A over P and B over 11 minus 2P, okay? So you split the factors up to do different fractions, and then I can say, well, A of 11 minus 2P, and then bringing the fraction together, you add them, BP over P of 11 minus 2P. And then that's the exact same fraction here, but the numerator has to be 1. So therefore 1 has to be identical to A lots of 11 minus 2P add BP. Now we need to solve for A and B. So you can compare coefficients. So this is also saying 0P add 1. So you can compare the coefficients for P, but you could then just let substitute various values for P in. And the best way is to cancel the brackets. So first of all, BP, if P is 0, that would get rid of the B. So you're left with A of 11. Well, 11 minus 2 of 0 is just 11 equals 1. So therefore A is going to be 1 over 11. And then I'm going to say then let P be, well, 11 minus 2P is 0. Therefore P is going to be 11 over 2, right? Yes. So I'm going to say 11 over 2. Therefore, what? 11 over 2b has to be 1. So therefore, b, because the a will cancel out then. Okay, because the bracket was 0. So 1 divided by 11 over 2 will get me 2 over 11. Cool. So therefore, there we have it. Partial fractions then. 1 over p, 11 minus 2p is going to be what? Well, a is 1 over 11. So that's the same as, say, 1 over 11 lots of p. And then b is 2 over 11 lots of 11 minus 2p. And that's your partial fractions done. Cool. Then part B. Let's have a look. The population of meerkats been studied, and we got this differential equation. P is in thousands. Like I say, remember, always highlight the units. Like in this case, the thousands. I think that's going to catch me out potentially. And T is time in years. Okay. There are 1,000 meerkats at the start. So when T is 0, P is going to be, well, is it going to be 1,000? No, because it's in thousands. So it's going to be 1. Because then 1 times 1,000 will indeed give us 1,000. So P is 1 there, not 1,000. So that's why you underline the the units in modelling questions. Okay, so we're going to need to solve. So that's to bear in mind. We're going to need to solve it, right? So when you see differential equation, you're probably going to solve it, but they don't just give it for no reason. So let's just write it down. So it's going to be 1 over 22, lots of p. Okay. And the first step is going to be again, get rid of the dt. I want one of each variable on either side. So I want the p on the left and the t bits on the right. So dp is going to be 1 over 22p. 11 minus 2p, lots of dt. Okay, cool. And then I want to get the p bit to dp, right? I want the p's together. So I'm going to times then by divide by 1 over 22p. So then therefore 22 p 11 minus 2p dp is going to equal 1 dt. And then I can then integrate both sides, right? So then therefore I'm gonna say integral of 22p lots of that, but then I'm gonna bring the 22 out because I just don't like. I don't know. I find it a bit messy having multiples of integral. I don't know. I find it a lot cleaner. Me personally, and that's gonna be integral of 1 dt. Okay. Okay, well, I can't integrate. Well, no, sorry. That's going to be 22 over p. I was about to say, why do we bother doing partial fractions? That's integrate nicely. Just expand it. No, I didn't. No, that would be then 22 over p lots of 11 minus 2 because I'm dividing by it. So therefore, that would become 1 over p lots of 11 minus 2p. And then well, I can't integrate this directly really, but I can use the partial fractions, can't I? So it's going to be 22 lots of 1 over 11. If I was then substitute the partial fractions in, 11 plus 2 over 11 of 11 minus 2p, right? Yes. And then the integral of 1, it's just going to be t. Add some constant c, right? Plus c. Okay. Wow, I'm going to split this up then. But firstly, I'm going to split this into two different integrals, right? I don't know what these factors I've got here. So, I can say the first bit is 22, and I'm going to pull out a factor of 11th, okay? So 22 over 11 of the integral 1 over p looks a lot simpler, doesn't it? dp, and then I'm going to say 22, and then I'm going to say and bring a factor of 2 over 11 over the 1 over 11 minus 2p, which again looks a lot simpler. So I pulled a factor of 2 over 11 out, and that's going to be t at c. And then I'm going to integrate now because it looks a bit nicer for me. So 22 over 11, first of all, is just 2. And then 1 over p integrates to learn mod p, okay? Remember modulus integration because you need to account for a negative. More specifically, 1 over p, the p differentiates exactly to 1. So it's just going to be the ln of the denominator. And then 22 times 2 over 11, so that's going to be 2 times 2, that's going to be 4. Lots of the integral. So this will integrate to, and now we need to check the bottom bit. That differentiates to minus 2, but we want 1. So we're going to need to account for this by then dividing by minus a half, okay? Because then minus a half times minus 2 will get us back to 1, which is what we wanted. So we're adjusting for that factor there. So minus a half ln then of 11 minus 2p. And that's again going to equal t at c. And then let's simplify it a little bit more. So 2 ln mod p add minus. So then that's going to be minus 2 ln 11 minus 2p equals t at c. And immediately I notice if I then divide by no, actually I'm going to leave it there for now. But I was going to say I did notice you could then factor a 2 out and then so learn p over 11 minus 2p because then that's learn p minus learn 11 minus 2p and then I can use the log law and that's going to equal t at c. Okay, I'm going to leave it there for now. But now is that what's it asking? It wants the time for the population to double. So really, we need to find to use our function to find the value, but we have a plus c. We have an unknown constant, so we're going to have to use this initial condition. So we're going to have to sub in t0 p is 1. If it lets me. P is 1, sorry, not c. So therefore, this equals a bit weird because there's already an equal there. So therefore, 2 ln of 1 over 11 minus 2 lots of 1 is going to equal 0. Well, it's 0 at c, so that's just going to be c. So really, c is just this log here, so we're going to have to simplify it. So it's going to be 2 ln, well, 1 over 11 minus 2. We'll just go to a ninth. So that's really the value of c there. Does it ask for any decimals or that? No, uh, no. Let's leave it in exact form. Okay, cool. That's c's to learn minus naught. But then it said the time taken for the population to double. So remember, initially p was 1. So for it to double, we needed to go to 2, right? 'Cause 2 times 1 is 2. So we need the time. So therefore, we can then say, well, t is going to be 2 ln of mod of 2 over 11 minus 2 lots of 2 minus c. So it's going to be minus 2 ln a ninth. Okay. Because all I'm doing here, by the way, is rearranging this for t. Because then t would be 2 ln of the whole modulus, the logarithm minus the c. Okay. I'm just rearranging that. And so once I've done that, plugged in p is 2. It's asked to give it in years. And t's in years, so yeah, let's just take the decimal. Okay, we can just solve it then. So to learn, I'm not I'm not sure if it wants an exact answer. I don't think it does in this case. Yeah, you wouldn't get a nice. Well, no, we could do. We could then say it's 2 of. Then learn. This simplifies to 2 over 7. And then minus learn a ninth. So you're going to divide by 9, a ninth. Okay. Or times by 9. Okay. Because I'm doing then this bit simplified to 2 over 7, and then this and then I factor 2 out. So then 2 over 7, learn 2 over 7 minus learn a ninth. You can divide them. So divided by ninth is times it by 9. So that would be to learn 18 over 7. And so in years, that's going to be, well, as a decimal guess, to learn 18 over 7 will be 1.8889, blah, blah, blah. So that's going to be 1.89 years, I guess, to 2 GP. Okay, but we gave an exact answer, I guess, as well. But does it say to round it? I don't know. I guess that's fine. But I gave the exact answer, I guess. Don't know. There we are. And that's in years. So that's in years as well. To learn 18 over 7 years. Okay, cool. Okay, that's quite a nasty integral. It's good to do this, right? Then part C shows that P is this. Okay. Right. Okay. So what's that asking us is now that we found C, we need to find an expression for P in terms of T. So I think um, if we then substitute C into here, um, we're gonna get 2 ln mod P. Oh, minus 2 ln 11 minus P. By the way, I'm talking about this section here, this line here. I'll highlight it actually. I'll box it. That's what I'm trying to deal with first. And then minus C, so that's going to be minus 2 ln a ninth. And that's going to equal T. Okay, so what we need to do then, what's going on here is P is on its own. So essentially, we need to get P just in terms of T. So the best step forward first is to simplify all these logs. Now notice all of these are multiples of 2, so then I can get rid of it to say ln mod P minus ln of 11 minus P minus ln of a ninth is equal to a half t, right, divided by 2. Then I can bring them all together. By using the log rule, so ln a minus ln b is ln a minus b, a over b. So I can bring this all together now, say ln of p over 11 minus p, and then I'm divided by a ninth. But that's going to be the same as times it by 9, so I'm going to get 9p, okay? And that's going to be equal to a half t. Okay, now I can raise it to e, right? So then I could say e to the ln of that is e to the half of t, but e to the ln of x for any x is just x, right? So that's simply saying the bracket bit of mod 9p over 11 minus p is e to the half of t. Okay, okay, now, notice there's no modulus brackets in the answer. So at this point, let's think about what's going on. E to the anything is always going to give like a positive answer, right? So that will always be positive. But P is between 0 and 5.5. Okay, that's the key point. So I'm gonna so if P is between 5.5, 0 and P of 5.5, then 9P over 11 minus P is always going to be positive, right? Well, it's always going to be greater than or equal to 0. But it's also going to be positive because the only time this is negative, if B is positive, is if 11 minus P, well, if P is 11 or more. Okay, but here P has to be less, well, is less than 5.5, so P is always less than 11. So this means 11 minus P will always be positive, and P will always be positive, so therefore the fraction will be positive for any P in this range. So therefore we can just knock off the modulus because it will always be positive anyway. So therefore 9P over 11 minus P is e to the half t. Get rid of this here. There we go. And then, well, so I got rid of the modulus because it's always positive anyway. We discussed that here. Then we just need p, so I need to rearrange for p. So therefore, 9p is going to be 11 e to the half t minus p e to the half t. So I'm times it by 11 minus p. Sometimes the e to the half t by 11 minus p, which I've done here. Okay, then I can rearrange a bit more. See. Then I can rearrange it to get p's on one side to say, well, p of 9 add e to the half t is going to be 11 e to the half t. Therefore, p then is going to be 11 e to the half t over 9 add e to the half t. Okay, so we've got p now on its own in terms of t, but we need it in this form here. And what I notice is there's only one e to the t term, there's only one exponential term, and also it's minus a half, not a half t. So what that implies is actually let's times then by e to the minus a half t on both sides. So then I'm going to be left with 11e, well, 11e half t times by e to the minus a half t. That's just going to go to 11, isn't it? Because e to the half times e to the minus a half would be e to the 0, wouldn't it? Because a half t add half t add minus a half t will cancel to 0. So e to the 0 is 1. So 11 times 1 is 11. Okay, so the top bit then will just go to 11 over 9 e to the minus half t. Know what you can do there. And then e to the half t times e to the minus will be plus 1, right? Because that will go to e to the 0, which is 1. So then I can say that's 11 over 1 add 9 e to the minus a half t. And now, is this in this form here? Yes, it is. It's in the form a over b plus c. So a is 11, b is 1, c is 9. So now we got it in the form they wanted. Okay, a would be 11, b would be 1, c would be 9. Okay, cool. That's a monster question, that is. But there we are. Oh, hang on. I'm off somewhere. Hang on, I need to check my answer. What have I got? What have I done here? Oh, half. That's what I forgot to include a half there because it's a half t. No, I didn't. Sorry. No, that would be e to the half. So the 9p would be 11. Uh, oh, that's where I've gone wrong. For some reason, yes. Part C. Yes, sorry. 11 minus p should be 2p. I don't know why. Okay, sorry. So it's not 11 minus p, it's 11 minus 2p. Yes, 'cause that's the denominator. Yes. So then that will go to easily adaptable though. 11 minus 2p will go to then 11 minus 2p. And for the same way, 11 minus 2p. So this is 0 when p is exactly 5.5, okay? So then when p is less than 5.5, it's still going to be positive. So it's still going to be positive fraction. So we can still get rid of the modulus, okay? So that's then going to be 11 minus 2p. Some p lots of p 9 of 2e. So then p is going to be times by 2e to the half t. Again, we still then times by e to the minus half t, so that'd be 11, then 9e, and then we have 2e to the half t times e to the minus a half. So that's going to be, I don't have room for it, 2e to the a half t times by e to the minus a half t. That will still give me e to the 0, and then I'm times it by 2. So this will be plus 2, not plus 1, because of the fact for some reason there was 11 minus 2p here, but then I just decided to knock the 2 off for some reason. Uh, yeah, I don't have a lot of space, that's my excuse. So it's messing up my writing. That's my excuse. So A is 11, B would be 1, and C would be, no, B would, no, then that would be 2 here. If it lets me go 2 here, so B would be 2, and C would be 9. But that is the answer. Okay, question 17 then, second to last question. A student attempts to answer the following question. So this is a proof of contradiction. Given that x is obtuse, prove this, and they're giving us the first line to work with. So we need, so they're giving us even the assumption statement, so we don't need to do that, but it would be the opposite, okay? So if x is the opposite, would be if x is obtuse, then the inequality would reverse. So it'd be sin x minus cos x is less than 1, which is what we've got here. That's the assumption. And then they squared it, okay? And it's still less than 1. Well, let's complete. So sin x minus cos x is squared, is less than 1. Okay, well, the good idea would be probably to expand it, right? See what we can do. So then that means, if expanded, it'd be sine squared x minus cos x sin x minus another cos x sin, it'd be minus 2 sine x cos x. and then minus cos x times minus cos x be plus cos squared. Again, if you're unsure of the bracket, you can spend a bit of time to expand it if you're uncomfortable. So do it something like this, right? So sin x minus cos x, and then it's repeated, so it's going to be another sin x minus cos x, and then use your normal methods, right? This and then times by this, and then this times by this, and then you get the same result that I've got here. But hopefully you can work that fairly quickly, and you get this, and that's going to be less than 1. Okay, now we can tidy this up because we know some trig identities, don't we? We should do. And the first one is actually sine squared x and cos squared x is 1. So that's going to give us 1 minus 2 sine x cos x. It's going to be less than 1. And I'm making use of the fact that sine squared x and cos squared x is always 1. So that's what I've done here. Then I can say minus 2 sine x cos x. Well, take away 1 from both sides, going to be less than 0. But I don't want this minus 2 here. I can divide by minus 2 to say then sine x cos x. Actually, no, sorry. No, let's keep the 2 because it looks like another identity. But I want to get rid of the negative. So 2 sine x cos x. And then we reverse it, right? Because we're divided by negative. So we get greater than 0. Cool. Now, I recognise this goes to another trig identity, but it's a double angle. It's sine 2x, isn't it? Because then that's going to be 2 sine x cos x. So this one can rewrite as sine 2x is greater than 0. And that looks pretty simplified to me. And we only got one bit of x. So like I said before, because we only got one x part, it's a lot easier to see the range, right? To see what values we can have. Whereas before we had 2 parts of x, so it's a lot harder to see where it goes to. But now we got 1. That's lovely. By the way, if you're unsure of this, if you're unsure to derive the double angle in the exam, you know what sine a plus b is. That's in the exam. Then just set a and b to be x, right? So then you're saying x plus x is 2x, and then you just substitute a and b for x. But I'm not going to go into that here. Okay, so we've got here, but where can we go from here? So it's really asking us to consider the range of sine of 2x, right? So it's going to look a bit like this. But we need to consider the range, but we don't know what range of values of x to take into until we read the question. We are given this bit here. They give us this for a reason. X is obtuse. What does that mean? If x is obtuse, then it's going to be between 90 and 180, right? It doesn't specify if it's radians or not, so you can take it either way. The proof will hold exactly the same way though. So that's between 90 and 180. That's an obtuse angle. Obviously, 180 or more is going to be reflex. If it's 90, it's a right angle, and less than 90 is acute. So that's x, but here we have sine of 2x. So this is a sine graph, by the way. So therefore we need to double the range, right? So it's going to be between 180, right? So we need to consider 180 to 360. So if we label it then, well, actually, I don't think we needed to double it because, oh no, we did, didn't we? Because we have sine 2x. Okay, what would the graph sine of 2x look like? Well, you're halving it, aren't you? Because it's a factor. So you have 2 in here, coefficient. So you're halving the x coordinates, aren't you? So that's sine of x. So then sine of 2x would be essentially like 2 different waves, wouldn't it? So then that'd be 9. No, no, that would be 90. That'd be 180, 270, 360. But it can still be above 0 between 180 and 360. Um. No, 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 no. Okay. So what I've considered is this is the sine graph, right? Sine of x. But 2 of x, I don't have to draw sine of 2 of x. But I can. But if I want to consider 2 of x, I then just double my range, right? So I can consider the graph sine of x, but that's equivalent to considering if I want 2 of x instead of x, I can use the original sine graph, but instead of between 90 and 180, I need to account for the fact it's double by going between 180, which is going to be here, and 360. Okay. Alternatively, I could consider the graph sine 2 of x, but then it would only be between 90 and 180. So if I 2 of x again would look like this sort of graph here. But then this would be 90, and this would be 180. So yeah, there we go. Okay. So you pick your poison. So sine of 2 of x, but then 2 of x has to be exactly between 90 and 180, or x. But then because we have two lots, because remember the original x, right, is obtuse, but we have 2 of x here. So we need to consider sine of x, but then double the interval, or we have sine of 2 of x. Uh, Obviously, then we need to consider this. I don't know. Hopefully, it made some sort of sense. But we can use the original graph of sine of x, but then because x is between here, we need to consider 2 of x, which is double. Okay, so we need instead of between 90 and 180, we need to consider 180 to 360. But we can use the original graph. There we go. Okay, so we got this. So that's our range to work with. So that's 2 of x. Okay. But what do we notice about sine of if we for any value, if we plug 2 of x here, so 2 of x is between 180 and 360. If we plug any value of angle x between these values, right, 180 and 360, um, what 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 can we deduce from this graph? It's always going to be exactly below 0, isn't it? It's going to be negative because look, this whole bit between 180 and 360 here. So that's 180 and that's 360. This whole bit when it's below, in this range here is always negative. But hang on a second, we're saying it's positive. How? So that's a contradiction. So we could say this sign here for contradiction. But uh, but for 180 to 2x to 360, sine of 2x is less than 0. I guess, for example, e.g., consider the graph, I don't know, y sine 2x or something like that. I don't know. I've drawn it here though, right? Uh, uh, I'm gonna say so I'm gonna say sine 2x is less than 0, uh, because I don't like that reasoning. I'm gonna say because the graph sine x or y sine x is negative between 180 less than 2x to 360. So obtuse values of x, right? So that's a contradiction. Therefore, assumption must be wrong. I'm going to say as we have a contradiction. And that's the whole idea, right? So that's the whole idea of the proof or contradiction. We make a single assumption here. So all we did was reverse inequality. Then we did some maths. The maths was right, but then we still got something wrong afterwards. So that means if all the maths was right, the only thing really changed was the assumption, and the assumption has to be wrong. So that means the opposite must be right. So therefore, uh, that means this statement has to be true. So sin x minus cos x has to be greater than or equal to 1. For obtuse x, I would say, just to be specific. And there we go. It's only 3 mark. I put it there. Uh, yeah, so there we go. Cool. Uh, I guess to clarify once more on this graph a bit, because even I was a little bit confused. If we have sine of x, right, the reason why we can just consider sine of x and not sine of 2 of x or whatever, sine of x we can consider that, I'll also draw it here, but as long as we adjust the range like of x like this, we can still use the normal graph of sine of x, which as long as we use the adjusted values, because it's essentially like saying you're plugging 2 of x for x, aren't we? We're saying like for these values, we're plugging in sine of 2 of x, which is what we've got here, sine of 2 of x. But obviously with these values of x, of 2x, right? So we can consider the graph, which is essentially like saying x goes to 2x now, but between these values. I don't know if that makes any sense. But yeah, so we don't need to consider the graph of sine of 2 of x exclusively to sine x. We can just use sine x as a graph, but then replace x with 2x. Does that make any sense? Rather than drawing a whole different graph of sine of 2 of x. Uh, but yeah, I don't know. Hopefully it made some sort of sense. But there we go. Final question now. Oh God, I've been on here for ages. I do want to wrap this up quite quickly because I want to get this onto YouTube for before the exam tomorrow to give people enough time to do whatever they want with this video. Anyway, so final question. I think it is important to go over this as well. They might ask a similar sort of question, and it is quite tricky. So we're given a curve, we're given a parametric. So parametric differentiation might come up. So be prepared. And we're given the line L here, which is normal. So think about gradients at the point where t is pi over 4. We need to find L essentially, first of all, using parametric differentiation. So, how would we normally work out a normal line? Well, you're going to need the tangent because the tangent here would then be perpendicular. So we need the grade of a tangent. So now how do we find a grade of a tangent of a line? Well, it's going to be dy dx, isn't it? But here, the x and y are separated. It's in terms of t. So we need to do parametrics. So we can alternatively say dy dx, we can say is dy over dt over dx by dt. And you can think of it as then the dt's cancelling, which will then give us back dy dx. But we can kind of give an indirect way of getting dy dx using t that way. Cool. So now we need to compute this. So, first of all, I'm going to say, well, y is 2 sec squared t. I'm going to say this is 2 of sec t squared at 3. I'm going to write it in a specific way because then dy dt, I can then, is hopefully you can see, you can use the chain rule. And actually, you do not need to know how to well, unless it asks you to prove it. But you don't need to just always know what the derivative of these trig functions are because they're in the formula book. Although you do need to know how to interpret it. So they're given it like this. But I know this is sec of x, then the derivative is this. But then I have sec of x, so it's just going to be k1. So then the derivative on k1 here, if it lets me, is going to be sec x tan x, okay? So so it's going to be 2 lots of, and then the derivative of sec x for any x is sec x tan x, as we saw. So we need to differentiate. So we need to times by the power first in the brackets of 2. Then I need to differentiate the bracket. So that's going to be sec t tan t. And then I need to knock one off. So 2 minus 1 is 1. So it's just 1, right? So it's itself. So that's the derivative of y with respect to t. Now dx with respect to t, we have 2 tan t add 1. So, and then plus 3, by the way, will cancel to 0 because it's a constant. Now dx dt, again, tan is given here. So when k is 1, tan x will go to sec squared x. So simply, the derivative is going to be 2 sec squared t. Okay. Yes. So then I'm going to plug these both into here, the derivative, to then get 4 sec t tan t over 2 sec squared t. And the 4 and 2 will cancel, be 2. And then we'd be left with tan t over sec t. I feel like that should cancel, no? I don't know. Did I differentiate it right? Yes, I didn't. No, because that's why. Dy dt 2 of so yeah, so 2's the leave the 2 out the front. Then I differentiate. So times by the power, which is 2. Then I differentiate inside. So sec t goes to sec t tan t. Then I have sec t 2 minus 1. So inside the bracket, knock 1 off. Well, that's just 1. So we need to add another sec t. So that's going to be sec squared t tan t. So then the sec squares will cancel. And we're left with 2 tan t. There we go. I forgot to include that extra tan t. But yeah, like I said, if you are a bit stuck with the chain rule, especially for a question like this, don't be afraid to use the U sub and say like U is sec t, and then do it like the more formal way and split it, do it step by step. I did it all in one go, but yeah. Okay, so that's 2 tan t, that's dx, so therefore dx, sorry, dy dx at t is pi over 4 because they're giving us that. It's going to be 2 tan of pi over 4, which is just going to be 2, I think. But let me check that. I'm in degrees again. Let's change it back to radians. That's going to be 2. Yes, 2. Okay. So that's a derivative. So therefore, therefore the gradient of a tangent is going to be 2. So therefore, the gradient of the normal, so m, is going to be minus a half. Because parallel lines, obviously, their gradient will be negative reciprocals. So take the reciprocal, 2 is a half, then minus it to get minus a half. So therefore, the line of the normal is going to look like y is mx plus c. So it's going to be minus a half x plus c. Okay. Now we need to find a point on the normal to find c, but we know a point, don't we? It's at p, and p is when t is pi over 4. So let's then substitute t. So when t is pi over 4, then x is going to be, first of all, we can get the x and y coordinates. So that's going to be 2 tan pi over 4, add 1. So that's going to be 3, because then that will go to 2 and add 1. And then y is going to be 2 sec squared of pi over 4 plus 3. And then plug that into your calculator. And you might have sec on the calculator, so you could then say 2 times this 1 over cos squared of pi over 4. So cos pi over 4 all squared, and then add 3 to get 7. Okay, so that 2 sec squared pi over 4 is 4, then add 3 to get 7. That's in the calculator. So I don't think there might be a sec on your calculator. So what I did, you need to remember sec is 1 over cos. So then you need to do 1 over cos squared, which is 1 bracket cos of pi over 4, then square it. Okay, that's the way to write it on the calculator. So I've got these values then, they're quite nice actually. So therefore, sub x is 3y7. So therefore, at 7, it's going to be minus a half of 3 add c. So therefore, c is going to be 7 add 3 over 2. It's going to get us 17 over 2. So therefore, y is minus a half x add 17 over 2. And that's what they got there. Lovely. Then for part B, again, fairly typical parametrics, show that all points on C satisfy this equation here. Okay. Now, we're given all the numbers, so I think we can just probably substitute x in directly, and in terms of t, obviously, and then eventually we should get this for y. Let's try it then. So, firstly, the best way to so let's consider half of x minus 1 squared plus 5. That's going to be half of then x minus 1. It's going to be 2 tan t add 1 minus add 1 minus 1. Squared add 5. But obviously the ones will cancel, so we're left with half of 2 tan t all squared plus 5. That's going to get us 4 tan squared t, but 4 divided by 2 is 2, so it's going to be 2 tan squared t add 5. Okay, but this is in terms of sec though for y, so we need to get this tan to a sec. But we know an identity that links them, don't we? So we know that 1 plus tan squared t is sec squared t, okay? If you are a bit stuck remembering these ones, obviously if you remember, and you should know that cos squared t and sine squared is equal to 1, you can divide, there are two identities you can get from this. You can divide by cos squared on both sides, so then that'd be 1 plus sine squared over cos squared would be tan squared. And that's going to be 1 over cos squared, which is going to be sec squared. So that's the identity we've got. Alternatively, you can then divide by sine, and you should get 1 plus cot instead. And that'd be cosec. But you can get, if you know the normal one, cos squared and sine squared, if you divide by each of cos or sine, you get the other two as well that you need to remember. But that's the identity we're going to use. So therefore, 2 of tan squared, well, that's going to be 2 sec squared t minus 1 plus 5. So that's going to be identical. So it's going to equal 2 sec squared t minus 2 add 5. That's going to be 2 sec. Oh. 5 minus 2 would be plus 3. And actually, that's now equal to y, because y is 2 sec squared add 3. Happy days. Therefore, Therefore, to reiterate, y is a half x minus 1 squared add 5, which is what they want us to show. Great. Okay, cool. So that can be a strategy, right? To substitute x in and then do some manipulation and eventually get the y or whatever they want to show you. Okay, now here the final question, but here is the killer. And actually, this actually is quite similar to the modular stuff we did before, when you consider different lines. Let's have a look. Then it says a straight line with equation y is minus a half x plus k intersects the curve at two distinct points. Find the range of possible values of k. Okay. Again, let's try and plot this line, and then see how it matches with the curve on the graph. So minus a half x plus k. But actually, L is minus a half x plus 17 over 2. So the L has the same gradient as this. So this line, this general line, has to have the same gradient, so it could look like this, or this, or this, or this, going up and down. But the c will change. But the c is essentially adding a number on top, right? So that corresponds to moving up or down in the y direction. So essentially, if I get a ruler again, it probably bug out probably, but let's try it again. If we then match the same gradient of the line of L, this is going to be an absolute mess. This is. Yeah, it's not going to work. But essentially, that's some sort of strategy, right? You want to. Yeah, this line is bugging out. But essentially, again, consider lines that are the same gradient, but then you shift it up or down. So essentially, they give you an example of a line already. That's L. So then if you match the gradient of L, then you can just use your ruler or whatever to visualize. Imagine it's shifting the line up or down, because that's what the plus C is doing. It's essentially shifting the line with the gradient minus a half up and down. Okay, there we are. We're getting close to it. A bit closer. There we are. There we go. So that's L, right? Now, what C's doing is literally shifting it up or down. That's the only thing we can do by adding C. So what happens then? We can use this to visualize. And lucky you should have a ruler in your exam, so it shouldn't be that bad. To see where it intersects with the curve. Okay, and in particular, it's asking for two distinct points with the curve. So we need two intersections. So if I move it down again, well, with this ruler, where am I going to get two intersections? Well, at L, there's only one intersection with the curve. If I go any higher, it's still going to be one. And then eventually it'd be none at all, right? Because it will go above the curve. Okay, then what about if we keep going down? Well, it's still going to be one intersection, but actually, eventually, ding, 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 it then hits this left part here as well. Oh, it hits this left part of the graph, notice? So if we line it up with, here, let's do it here. If we line it up here with L, with the same gradient, but then we shift it down, eventually it's going to hit the left part of the curve as well. And it's particularly going to hit it at the most furthest away point here, which I circled again. So it's going to hit it particularly at this very end here, right? So bear that in mind then. So it first hits it there. Okay, then if what that gives us two intersections then. Then let's keep going down. And then we're going to get two intersections with the left and the right side of the curve. Then eventually it's going to leave the curve, and then it's only going to intersect once and none at all as we keep going down. So it intersects somewhere like there, doesn't it? And then at that point, that's when there's one intersection, and then there's none at all. So really, our gradient, well, not our gradient, sorry, our C value, we have to shift it such that C has to be between here when it first crosses the left part of the curve, and then C values here are fine until then it hits the bottom of the curve once, and then it leaves off. So then we just need to find these 2 points that are circled, really. So let's go rid of the number line now. Hopefully that made sense. But we need to consider these 2 points. Let me zoom in then. And that's a general strategy, right? In general, these sort of line questions. Use your ruler to help you visualize what's going on. Anyway, so firstly, we need to find this point here, and then we discuss C. And when C goes down, then we have 2 intersections. Until then, and then it hits this bottom point here, and then it goes to 1, and then no intersection. So we need to find this point here. This is the furthest on the x. This is the furthest x coordinate to the left, right? Hope you can notice that. How are we going to get that? So I'm going to label this point 1 and then point 2, okay? These are the 2 points we need to consider with this line and the curve. Okay, so let's do 1 firstly. I'm going to do it up here. Firstly, x needs to be as small as possible to obviously get the furthest negative value. Well, actually, in this case, it's going to correspond to the lowest t value. So t is going to have to be minus pi over 4 to get this x value that's furthest away. Okay. And you can see that as well because, again, if you're not convinced, tan x is basically tan of x, right? Really. And a tan graph looks like this. So then between minus pi over 4, which is about here, and pi over 4, which is here, well, the tan of x is smallest at minus pi over 4. So that would give us the smallest x value. So then x then would be 2 tan pi over 4 minus pi over 4, add 1, which is going to get, that should be minus 1, I think. Yes. And then a y value. Y will find x and y, because then I can substitute it in. Because this line will then touch at the end point here, right? So it intersects. So we need x and y to substitute to find c. Okay, that's what we're doing here. God, let me get rid of this. There we go. Then y then is going to be 2 sec squared of minus pi over 4. Add 3. And that's going to get us 1 over cos of pi over 4 minus pi over 4 squared. Oh, I've got a syntax error. What's going on here? Oh, I didn't add a bracket. There we go. There we go. Got 4 and add 3. You get 7. Okay, cool. So then we're going to sub minus 1 7 into our line, right? Y is minus a half x plus c. I could have wrote it down downwards, but I don't want to scroll down just yet. So therefore, then 7 is going to be minus a half of minus 1 at c. So therefore, I'll write it down here. C then is going to be, well, 7. Well, this will go to minus a half times minus 1 will be positive a half. So you're going to want 7 minus a half. So that gives a c value of 13 over 2. Cool. So that, and as we discussed, that's the high C value because then we have to go even deeper downwards to then ensure that's the first point where we get to intersections with the line and the curve. Then we have to go move it downwards to keep getting 2 intersections as we saw with the ruler. So therefore C is going to be less than and equal to 13 over 2 because 13 over 2, remember, is when it crosses this end point here, but it's still going to intersect the end point and some other point on the right side. So that's when it hits 13 over 2, it will have 2 intersections. So it has to be equal to 13 over 2 as well. Okay, because it hits the end point as well as another point on the right side of the curve. Okay, so that's one value. So that's point 1. Then, as we discussed, then the final place where it has 2 intersections, and more specifically, then it gets to 1 intersection only. It's this here, this little bit on the bottom of the curve. How are we going to work that one out? You might think it looks perhaps at the turning point. You might be right, but we do not know that for sure. But a safe way of doing it as well, that's going to, when it goes between 0 to 1 to 2 solutions, that's going to be the discriminant, isn't it? Because think about it, the because we have we can use part B, because part B gives us this quadratic relationship, right? So we can use determinant. Yes, no, not term, a discriminant. Thinking of something else. But then consider consider this. What's happened here is this is not the whole quadratic graph though, because this curve here is only it's got cut off this end of the quadratic graph, right, and this part as well. So in theory, say if we had this whole quadratic here for all values of x or y, whatever, say if the curve then intersected up here, then it will always have two solutions. No matter then, if we shifted the line upwards, it will have two solutions. The only time the line would only have one solution, again, is that same point on the bottom, and then it will go to no solutions. So we can still use the discriminant to work out where point 2 is, where the curve starts to lose intersections with the line. Because when the because this will still correspond to the curve on the given to us, right? Because this bit isn't chopped off, right? As we thought, point 2 is point 2, right? Point 2 is on the curve given. So we can still use the quadratic and the discriminant to work out where it becomes only one intersection with the line. Okay, so let's do that then. I'm going to do that here then. So I'm going to say y meant, remember. So we have this function in part B. Again, it asks us part B for a reason. It's going to help to visualize the quadratic or perhaps use discriminant. But again, our line also is going to be minus the half x plus c. Then we're going to substitute it in. So we're going to say minus the half x plus c. And then that's going to be half. And then we're going to expand this. So then it's going to be x squared minus 2x plus 1 plus 5. Then I want to get rid of the fraction. So I'm going to say minus times by 2. So I'm going to say minus x plus 2c and make it clear times by 2 times by 2. Then that's going to be x squared minus 2x plus 1 plus 10. Okay. Okay. Then I put everything to the right. So then we'll say x squared minus 2x. Add an x. That's going to just be minus x. Then I'm going to have plus 1 plus 10. That's going to be plus 11 minus 2c equals 0. And now we can apply the discriminant to this. So discriminant, well, we want to find the discriminant greater than 0, right? Because that'll give when there's 2 points of intersection. So therefore, b squared is minus 1 squared minus 4 of 1. 11 minus 2c has to be greater than 0. So therefore, 1 minus 4 of 11 minus 2c greater than 0. Let's expand this out. So slow. So then that'd be 1 minus 44. Add 8c greater than 0. Is that right? Minus 4 times minus 2 would be 8. And then 8c. Cool. So then 8c then would be 43. Because then 44. What's it called? 44 minus 1 would be 43. So the c would be 43 over 8. So that c value is corresponding. So when c is equal to 43 over 8, then that would correspond to point 2. So point 2 is when c is 43 over 8. Point 1 is when c was 13 over 2. Remember? Here. So actually, what that's corresponded to is saying the value of c, when we shift this line down, this L, which is gradient minus a half, if we then pull it to 13 over 2, then it intersects twice with the end point and then another point. And then if we keep shifting it down to then c 43 over 8, by the way, 43 over 8 is less than 13 over 2, so it is smaller. Then if we keep shifting it down to 43 over 8, then it will only give one intersection and then it will be 0. So that means C would also then have to be greater than 43 over 8 exactly, which is what we got here, right? So then let's combine it together. So then C has to be less than, no, sorry. C has to be less than or equal to, yes, 13 over 2. And C has to be greater than 43 over 8. and is important here. It's not or, it's both, okay, in this particular case. Because it has to be strictly between these two value points here, right? These point 1 and point 2. Okay, and that's it, right? Let me double. No set notation. Yeah, that's the range of values. There we go. And actually, oh, sorry. And then we can combine it as one. So then we could say, well, C has to be above 43 over 8. So 48 is less than C, but then C has to be less than or equals 13 over 2. And that should be your your range of values for C. Hopefully that made sense. I would go over that and make sure that made sense if you could, because that might come up at the end of paper 2, especially you want those top marks. I would try and make sense of this sort of question because it could come up. But I'm going to check that's right. It should be right. I might have made an error somewhere though, but let me check. And by the way, this why I say this because this also came up in 2022 paper 2, and there might be not copying, but they might take some inspiration, let's say, from 22 paper 2, like they've done with paper 1. So I'm just saying, be warned, But hopefully that made sense. Yeah, so it's between 43 over 8, less than C. Oh, was it K? I swear it was C, wasn't it? Oh, am I saying C because it's like the wine? It's K. Oh, okay. So replace every C with K. Okay, there we are. Okay. So between K and 39, yeah, that's the right inequality. Just the wrong letter. There we go. But it doesn't really matter, right? It's called a dummy variable. So it doesn't matter what the letter you use is, as long as at the very end you put the right letter at the end. And that's it. Okay, I am gonna. I don't see anything. I've been on here for ages. I didn't expect to take so long, but like I did, I tackled the more harder questions first. I feel like I took the harder questions from the papers I did, so it's going to take a bit long to explain and go over. Obviously, I had some mess, some. It wasn't plain smooth sailing all the way through. But I did want to take time to explain it. But I am going to leave it there to not go on any longer. Um, I'm going to upload this to YouTube now, before tomorrow afternoon. Well, immediately after the live, actually. But hopefully it doesn't take too long to export. But I'm going to leave that there then. Good luck with your exam for paper 2. After this, no more pure. But then you got stats and mechanics. So I'm going to have to brush up on that if I want to do more videos because even I'm not. But anyway, I'm going to leave that there then. Good luck. But yeah, hopefully this was of use. But I am going to leave that there then. See ya.